The story of the great insects is not just a tale of extinction. It is a profound lesson in the delicate balance of a living planet. Every breath we take, every stable night we enjoy, is a gift from a world that learned through fire and ice that the biggest is not always the best. The giants taught the earth its limits, and in doing so, they paved the way for the world you sleep in now. If you found peace in this journey through deep time, please consider supporting Tierra Hueca by giving this video a like, subscribing to the channel for more calm exploration, and leaving a comment below about what mystery you'd like to explore next. It truly helps this corner of the internet find others seeking quiet wisdom. Imagine a world entirely draped in green and black, a landscape that whispered rather than shouted, under a sky slightly different from ours. This was the era of the giants, and their secret was not hidden in myth or magic, but in the invisible medium that sustained them, the air. During the peak of the Carboniferous Period, roughly 360 to 300 million years ago, the Earth's atmosphere was undergoing an extreme transformation. Today, the air you inhale is primarily nitrogen, with a comfortable average of about 21% oxygen. In the world of the giant insects, that level soared. It climbed to an astonishing, life-altering height, settling in a range often estimated to be between 30 and 35% oxygen concentration. Think about that increase. It's not a minor adjustment. It's a radical biological engine shift. This profound concentration of oxygen, this breath of giants, is the single most critical factor in the rise of the enormous arthropods that define this era. To understand why, we must first look at the most fundamental limitation of the insect body plan. Unlike you, insects do not possess an active, centralized respiratory system based on lungs or gills. They rely on a more rudimentary and passive method, the tracheal system. Visualize a network of microscopic tubes or tracheae that branch throughout the insect's body. These tubes connect directly to the outside air through small openings on the exoskeleton called spiracles. Oxygen doesn't get pumped into the blood by a heart. It simply diffuses, it passively leaks from the high concentration of the outside air into the insect's internal tissues. For a tiny ant or a common housefly, this system is perfectly efficient. The distances are small and diffusion is fast enough. But as the insect's body mass grows, the distances the oxygen must travel become exponentially longer. At a certain point, the rate of passive diffusion simply can't supply enough oxygen to the internal organs and flight muscles to sustain life. They would suffocate from the inside out. The carboniferous air removed this barrier. With the atmospheric concentration of oxygen sitting at 35%, the pressure difference driving that passive leak was significantly higher. It was an invisible planetary hyperbaric chamber. This rich, concentrated air supercharged the tracheal system, pushing oxygen deep into the tissues of a body that, under normal conditions, would have been physiologically impossible. This is why the meganeura, a dragonfly with a wingspan of over 2 feet, could exist. This is how the arthropleura, a multi-legged millipede-like creature that could reach lengths of over 6 feet, could lumber through the damp forests. Their size was not an evolutionary miracle. It was a simple, logical consequence of atmospheric physics. The increased oxygen did more than just allow size. It fundamentally altered the entire ecology. The air itself became a source of enormous, easily accessible energy. The speed of chemical reactions was accelerated. The vast flight muscles required for the giants to hoist their tremendous bodies into the air could be saturated with fuel simply by opening the spiracles. In this world, gigantism was not an option. It was a highly favorable evolutionary pathway. Why stay small and struggle when the planet itself is encouraging you to grow? This era of supersaturated air lasted for tens of millions of years. It was a stable period where the massive flora, the ancient, bark-covered trees and giant ferns died and, crucially, did not decompose. Think of the endless, colossal forests locked in an ongoing cycle of life and death, where the decay process was radically slowed. The bacteria and fungi required for efficient decay had not yet evolved the metabolic complexity to break down the tough lignin in the new plant life. This meant that carbon, instead of returning to the atmosphere as carbon dioxide, was buried in massive quantities. Layer upon layer of dead organic matter was compacted, eventually forming the vast coal seams that define the Carboniferous Period, the very source of the name itself. This burial of carbon was the engine driving the high oxygen. As the carbon dioxide was sequestered away, the relative concentration of oxygen produced by photosynthesis rose sharply, climbing to levels unmatched since. The planet essentially built a prison for its carbon and unleashed its oxygen. The resulting environment created a world of immense stillness and almost alien perfection for the arthropods. The dense air made the physics of giant flight work. Imagine the drag helping to support the heavy wings. The rich oxygen fueled massive muscle exertion with ease, and the lush, damp forests provided the continuous fuel and shade necessary to maintain their bodies. This was the context of the giants, a direct physical manifestation of a unique planetary event. They were not just big. They were a living barometer of an atmosphere fundamentally different from our own. They represent a state of life that exists only when the Earth tips the scales of its own chemical composition. But nothing lasts forever. That stability, that perfect, rich air, was a temporary phase. And as we will soon explore, when the planet's geological engine began to turn again, the slow, silent process that created the giants would eventually and inevitably lead to their doom. The same air that gave them life would first thin, then turn toxic, leaving their massive exoskeletons as mere fossils in the dust of deep time. For now, simply rest in the image of that powerful, oxygen-heavy world, a time when the very act of breathing was a surge of energy and the skies belonged to dragons far grander than any myth. As we settle deeper into the tranquility of the Carboniferous air, let our focus narrow from the vast forests to the skies above them. If the high oxygen was the planet's invitation to gigantism, the creature that accepted that invitation most dramatically was the meganeura. Imagine for a moment the sound of its approach. Not the gentle buzz of a modern dragonfly, but a deep, resonant hum, a steady thrumming of wings spanning close to 28 inches, or about 70 centimeters, the size of a modern crow, but built entirely on the insect blueprint. This was not just a large insect, it was the largest flying insect that ever lived. Its sheer scale forces us to reconsider the limitations we place on the physics of the natural world. The meganeura's flight mechanics were a wonder, made possible by the unique density of its environment. In our previous chapter, we established the crucial role of 35% atmospheric oxygen in fueling the insect's internal metabolism. Now let's consider the external physics. The Carboniferous air was not only richer in oxygen, it was also denser than the air we breathe today. This is a critical point. While the absolute air pressure might not have been much higher than today, the molecular weight and composition of the atmosphere provided greater resistance. Imagine swimming through water versus swimming through syrup. When an organism tries to move a wing through a denser medium, that medium offers greater lift and drag. For a flying animal as large as the meganeura, this atmospheric density was its essential scaffold. Its wings were not simple membranes. Fossil records reveal a fine, complex network of veins and struts designed to maximize surface area and structural integrity. These wings were powerful hydrofoils, efficiently harnessing the dense air. Every downstroke encountered significant resistance, allowing the massive body to be lifted with far greater efficiency than would be possible in the thinner, 21% oxygen air of the present day. The meganeura was a sky hunter, a specialized voracious predator perfectly adapted to its rich skies. Its enormous compound eyes, suited for the dimly lit understory of the humid forests, would have granted it nearly 360-degree vision. It was the undisputed apex aerial predator, long before birds or even pterosaurs took to the air. Its prey were smaller, contemporary insects and potentially even early, small amphibians that strayed too close to the water's edge. The meganeura's hunting style required not just raw power, but unmatched maneuverability. This is where the supercharged metabolism comes into play. To execute the rapid twists, turns, and instantaneous stops characteristic of dragonflies, an enormous amount of energy must be delivered to the flight muscles instantly. The meganeura's massive flight muscles, housed in its thickened thorax, were constantly being bathed in oxygen at 3 times the modern partial pressure. This allowed for incredibly fast ATP, adenosine triphosphate, production, the fuel of cellular activity. This high metabolic rate translated directly into high G-force maneuvers and sustained high-speed flight, making it an efficient, unstoppable killing machine in the air. However, the nature of its respiration, the tracheal system, imposed a necessary limitation on its activity cycles. While the high oxygen allowed for large size, it didn't fundamentally change the passive nature of its breathing. Meganeura likely needed periods of quiet rest to allow the dense oxygen to fully diffuse into all its deep tissues, particularly after prolonged aerial chases. Imagine these giants settling onto the giant bark of a lepidodendron tree, their wings folded, the only sound the faint, gentle hiss of air exchanged through the spiracles, slowly recharging the massive muscle banks. The evolution of the meganeura also tells us about the absence of competition during this time. The Carboniferous was largely dominated by invertebrate life on land. The tetrapods, 4-legged vertebrates, were still relatively small and clunky, largely confined to the water's edge. This meant there were no high-speed, warm-blooded predators capable of challenging the meganeura's aerial supremacy. The world was fundamentally different. There were no bats to hunt at night, no agile, high-altitude birds. The sky was an open, oxygen-rich frontier, and the meganeura was the most perfect organism designed to exploit it. It represents an evolutionary moment, a niche saturation, where the limits of the physical and chemical environment were reached and exploited by a single, colossal blueprint. The sheer stability of the ecosystem also contributed to its reign. The lack of violent climate shifts and the continuous supply of high-grade atmospheric fuel allowed the creature to evolve its size over millions of years without the constant need for rapid adaptation or miniaturization, which would come later. But this very reliance on extreme environmental conditions was its fatal flaw. The meganeura's life was a function of the 35% oxygen atmosphere. Its gargantuan size was a physiological debt owed entirely to the abundance of fuel. It evolved no internal mechanism to compensate for a sudden drop in that fuel supply. It was a highly specialized, exquisitely tuned engine, running only on a specific, high-octane blend of atmospheric gas. When the planet's geology eventually changed that blend, the perfect engine of the sky would stall, unable to find enough lift or power in a thinning, altered air to sustain its massive dimensions. For now, let us savor the silent majesty of its flight. A creature of immense power, carving effortless trajectories through the dense Carboniferous skies, a living testament to a lost world where the laws of nature bent to the breath of giants. As the great wings of the meganeura settle in our imagination, we turn now to the true internal architecture that dictates all insect size, the tracheal system. This is not just a biological curiosity, it is the fundamental constraint, or, in the Carboniferous, the ultimate enabler of arthropod life. To truly grasp the gigantism of the ancient world, we must first understand the elegant simplicity and profound limitation of this respiratory design. Insects breathe not with lungs, but through a vast, intricate network of tubes. Visualize your body being perforated by tiny, evenly spaced openings called spiracles. These are the air intakes, essentially tiny, controllable valves running along the sides of the insect's abdomen and thorax. From these spiracles, air travels into larger tubes, the tracheae, which then branch repeatedly, forming a delicate, microscopic web of tracheoles that penetrate deep into every cell and every muscle fiber. Unlike the human system, where oxygen is picked up by blood in the lungs and then actively pumped by the heart throughout the body, the insect system is direct. Oxygen is delivered right to the doorstep of the tissue that needs it, bypassing the circulatory system entirely. This efficiency is why insects can sustain bursts of activity. They don't have to wait for blood to shuttle the oxygen. However, the delivery mechanism itself is largely passive, relying almost entirely on a physical process known as diffusion. Diffusion is the simple, slow tendency of molecules to spread out from areas of high concentration to areas of low concentration. In the case of respiration, this means oxygen passively diffuses from the highly concentrated air outside through the tracheal network and into the oxygen-starved cells inside. This reliance on diffusion creates an ironclad rule for insect morphology. The distance oxygen must travel sets an absolute limit on body size. Imagine the deepest muscle fiber in the center of an insect's thorax. The further that cell is from the nearest spiracle, the longer the path the oxygen molecule must passively diffuse along the tracheoles. The efficiency of diffusion declines rapidly with distance. It becomes an agonizingly slow, geometrically constrained process. In the modern world, with our 21% oxygen atmosphere, the diffusion rate imposes a strict size cap. The amount of oxygen that can be squeezed into the tracheal tubes simply cannot sustain the metabolic needs of a creature that is too thick. This is why even the largest modern insects like the Goliath beetle or the Queen Alexandra's birdwing remain relatively slender and compact compared to their ancient cousins. Their dimensions are defined by the need for all their cells to remain within a short diffusion radius of the nearest air supply. The Carboniferous air of 35% oxygen fundamentally broke this rule by dramatically increasing the partial pressure of oxygen outside the insect. The gradient, the difference in concentration between the outside air and the cell interior, was immensely steepened. This steep gradient acted like a powerful, invisible pump, forcing the oxygen to diffuse much faster and much deeper into the body mass. Suddenly, the insect could afford to be thicker. The deeper muscle fibers, which would have suffocated in a modern 21% oxygen environment, were now viable. The meganeura could develop the massive, oxygen-hungry muscle blocks required to move its gigantic wings, and the arthropleura could support the metabolism of its 6-foot-long segmented body. This was the strict prerequisite for their colossal size. Their evolutionary path was not limited by a slow accumulation of genetic changes, but by a sudden, sustained boost in atmospheric fuel. It was an environment that essentially said to the insect world, "You may grow as large as the oxygen can reach." Without this atmospheric supersaturation, any insect that attempted to grow beyond the modern limits would have simply stalled in its development, suffocating at the pupa or larval stage, or collapsing the moment it attempted to fly. It's important to note that some larger modern insects do supplement this passive diffusion with active ventilation. They compress their abdomens, a visible rhythmic pulsing, to physically push air through the larger tracheal trunks. This is a behavioral adaptation to squeeze a little more performance out of a low oxygen world. However, even this active pumping is a workaround. It doesn't change the ultimate limitation of diffusion at the final, microscopic stage, the movement of the oxygen molecule from the tracheole to the mitochondrion. The giant insects of the Carboniferous didn't need this struggle. Their world was one of metabolic ease. The sheer partial pressure of the oxygen did the work for them, transforming the simple, limiting tracheal system into a high-efficiency internal supply line capable of fueling giants. This deep reliance on the atmospheric gas concentration makes the arthropods a unique barometer of Earth's climate history. The rise of the giants wasn't just a fascinating anecdote, it was a direct, measurable consequence of planetary carbon sequestration. And as we trace the long, slow decline of the Carboniferous, we must remember that every millimeter of their size was tethered to the oxygen concentration, making them exquisitely vulnerable to even the slightest atmospheric change. When that chemical scaffold finally crumbled, it would not be the speed of a predator or the lack of food that killed the giants. It would be the simplest, quietest failure of all, the gradual inability of the air to reach the deepest, darkest corners of their once magnificent bodies. To truly comprehend the breadth of the giants, we must descend from the dense, oxygen-rich skies and enter the deep, silent realm that created them. This was the Carboniferous forest, a boundless, dripping, ancient ecosystem that served as both the engine and the tomb of the period's life. This world was the geological factory that systematically stripped carbon from the atmosphere, ensuring the giants had the fuel to thrive. Let your mind drift into this primordial landscape roughly 320 million years ago. Imagine an unbroken global swamp, not the patchy wetlands we know today, but a continent-spanning moisture trap. The light here is filtered and dim, penetrating through a dense, tiered canopy unlike any modern forest. Forget oak, maple, or pine. The dominant life forms were towering, non-flowering plants that bordered on the alien. Picture the lepidodendron and the sigillaria, sometimes called the scale trees or seal trees. These were not true trees, but colossal club mosses, rising straight and unbranched like telephone poles to heights of over 100 feet. Their massive trunks were covered in bark, patterned like reptile scales, shedding long, needle-like leaves from their crowns. The sheer scale of this flora was immense, but it was their chemical composition that held the secret to the oxygen surge. The plants of the Carboniferous had evolved a tough, complex substance in their cell walls called lignin. This structural polymer gave them the rigidity to grow taller than ever before, but it posed a significant new problem for the planet's microscopic recyclers. When these enormous trees died and crashed into the perpetually waterlogged soil of the swamp, they didn't readily decompose. Why? The microorganisms of the time, the fungi, bacteria, and decay organisms, had not yet evolved the necessary metabolic machinery, the specialized enzymes, to effectively break down this new, hardy polymer. This is the geological bottleneck that defined the era. In a healthy modern forest, fallen wood quickly breaks down and the stored carbon is returned to the atmosphere as carbon dioxide, CO2. In the Carboniferous swamps, this process was dramatically halted. Instead of decaying and cycling CO2 back into the air, the vast biomass was simply buried, sinking beneath the water and the rising mud. Layer upon layer of this pristine, non-decaying organic matter accumulated, compressed by the weight of the water and the sediment above. This is the material that over millions of years of intense heat and pressure transformed into the vast, dense black material we call coal. The Carboniferous period is named for this geological gift. It literally means coal-bearing. The formation of this massive global carbon sink had two immediate, radical effects on the atmosphere. Falling CO2, the burial of the carbon, removed a staggering amount of CO2 from the atmosphere, weakening the greenhouse effect and ushering in periods of global cooling. Rising O2, since the plants were still photosynthesizing, producing oxygen, O2, and using CO2, and the CO2 was not being recycled back through decay, the relative concentration of free oxygen in the atmosphere skyrocketed. The Carboniferous was, therefore, an accidental planetary-scale oxygen factory, The simple inefficiency of the ancient fungi created the physiological necessity for the giant insects. The damp, silent forest floor, where everything was eternally preserved, was the fuel source for the meganeura's colossal wings. Imagine walking through this forest. The air is thick and still, heavy with humidity and an intoxicating concentration of oxygen. There is no sound of small, rustling mammals, they haven't yet evolved. Instead, the air is filled with the deep thrum of giant wings and the immense silence of slow, waterlogged time. The swamps are so anoxic, so devoid of oxygen below the surface, that nothing can fully break down the material. It is a world of suspended animation. This ecosystem provided the essential stability required for gigantism. For millions of years, the process was self-sustaining. More giant plants grew, more carbon was buried, and oxygen levels remained high, allowing the insects to reach their maximum size. This ancient forest, which now lies compressed beneath our feet as the very coal that powers our modern industries, is a profound, silent reminder of Earth's history. The fact that any of us can light a fire with a lump of coal connects us directly to the moment the meganeura last took flight. For the fuel used to power our world is the very body of the forest that powered theirs. But as with all extreme planetary conditions, this state of equilibrium was temporary. The evolutionary clock does not stop. Eventually, new life forms would arise, microorganisms capable of solving the complex chemical puzzle of breaking down lignin. When the decay process finally caught up, the carbon sink would slow, and the ancient oxygen bubble would begin to deflate, setting the stage for the fall of the giants. For now, rest in the deep quiet of this primeval swamp. Feel the rich, heavy air, and listen to the silence of the undecaying world beneath the water. We have explored the gift of the carboniferous air and the monumental scale of the insects it produced. But now, we must turn our attention to the fundamental silent ruler of the microscopic world, the law of diffusion. This law, an unyielding constraint of physics, is the true, ultimate size regulator for any creature relying on a passive respiratory system. Understanding it reveals why the giants were living on borrowed time, even before the climate changed. Diffusion, in its simplest form, is the spontaneous spreading of molecules from where they are highly concentrated to where they are less concentrated. In the context of insect respiration, it is the process that drives oxygen from the outside air into the waiting tissues. This process, while essential, has a critical flaw for large organisms. Its efficiency decreases exponentially with distance. Imagine oxygen molecules as tiny messengers trying to navigate a dense city. For a short journey, they arrive almost instantly. But as the journey doubles in length, the time it takes to arrive doesn't just double, it squares. This is because the molecules don't travel in a straight line. They bounce and collide randomly with countless other air molecules. The overall distance they must travel to penetrate the center of a body mass becomes too great for diffusion alone to be effective. For an insect, this means that the deepest tissue, the core muscle fibers or the furthest cells, must remain within a short, non-negotiable distance of the end of the tracheoles, those tiny respiratory tubes. Beyond this physiological limit, the cells simply cannot receive oxygen quickly enough to sustain their energy needs, particularly for high-demand activities like flight. The law of diffusion therefore imposes an absolute biological size cap on all organisms that do not have an active, pressurized respiratory and circulatory system. This is why vertebrates evolved lungs and a heart to physically push oxygen via hemoglobin in the blood to every cell, circumventing the slow constraints of diffusion over long distances. The giant insects of the Carboniferous didn't evolve lungs. They found a temporary cheat code. As discussed, the atmosphere itself became the solution. By increasing the external oxygen concentration from 21% to 35%, the molecular pressure pushing the oxygen into the insect's body increased dramatically. This steepened the concentration gradient so much that it momentarily pushed the diffusion limit outward, allowing their bodies to grow thicker and larger than ever before. However, the law of diffusion itself never actually changed. The constraint of the tracheal system remained. Even at 35% oxygen, there was a point, a threshold, where the sheer distance across the tissue mass prevented further growth. This is why even the arthropleura, as vast as it was, maintained a relatively flattened wide body profile, ensuring its tissues were not too far from the spiracles along its many segments. This relationship between size and oxygen is often described using a simple geometric rule. When an animal grows, its volume, and thus its oxygen demand, increases by the cube of its linear dimensions, while its surface area, where the oxygen enters, increases only by the square. In simple terms, as the giant insect grew, its need for oxygen rapidly outpaced its ability to absorb it. The 35% oxygen air only delayed the moment when this imbalance became fatal. It didn't eliminate the fundamental principle. This vulnerability meant that the giants were exquisitely sensitive to even slight drops in atmospheric oxygen. A modern housefly could survive comfortably in air that is 15% oxygen, but for the meganeura, a drop from 35% to 25%, which still sounds high to us, would have meant an enormous reduction in the critical driving force for diffusion into its oversized flight muscles. The once life-giving, hyper-concentrated air would become inadequate. Their deep internal tissues, previously just barely supplied, would quickly become starved. The energy required for their powerful aerial maneuvers would become unavailable. Imagine a colossal, intricate machine designed to run only on a specific high-voltage current. The moment the voltage dips below a certain tolerance, the machine doesn't just slow down, it simply ceases to function. The giant insects were magnificent, but they were also a metabolic edge case reliant on a singular, fleeting planetary anomaly. As we move forward in the story of the giants, we will see how geological forces conspired to turn this delicate balance against them. We will witness how the slow, inexorable drop in oxygen, combined with the catastrophic rise in carbon dioxide, pushed their physiological limits inward until the vast dimensions that once granted them aerial supremacy became a crushing, unforgiving liability. The law of diffusion is a silent, constant truth. It waits patiently for the temporary exceptions to fade, demonstrating that in the end, size is not determined by ambition, but by the relentless, quiet efficiency of chemistry and physics. As we have seen, the extraordinary oxygen levels of the Carboniferous provided the internal fuel for gigantism, momentarily defeating the law of diffusion. Yet, another fundamental constraint of the arthropod body plan remained: the exoskeleton. This external armor, while offering superb protection, presents severe structural and metabolic challenges at massive scales, a colossal weight, literally on the shoulders of the giants, insects. Millipedes and all arthropods rely on this hardened shell for support, protection, and muscle attachment. It is an evolutionary success story for small creatures, acting as both skeleton and skin. However, as the giant insects pushed their body masses to extreme limits, the exoskeleton transitioned from a strategic asset to a debilitating burden. The primary challenge lies in the relationship between strength, weight, and scale. When an organism's size increases, its mass, volume, grows far more rapidly than the cross-sectional area of its supporting structure. This principle is often referred to as the square cube law. Imagine a modern ant. Its tiny, rigid legs are incredibly strong relative to its miniature weight. Now, apply this to a creature like the 6-foot-long arthropleura. To maintain structural integrity at that length, the external skeleton, composed primarily of chitin and protein, must be disproportionately thick. If the armor was scaled up linearly from a small insect, it would crumple under its own weight. The necessity of increasing the shell's thickness to prevent mechanical failure meant a massive increase in the overall body weight that the creature had to carry. This structural requirement created a paradox. The thicker the armor, the heavier the armor, which then required even thicker armor to support the initial increase in weight. The result was an arthropod body plan that was inherently less efficient than a similarly sized vertebrate. Vertebrates possess an endoskeleton, internal skeleton, which grows stronger and lighter because the muscles can attach to the inner structure, distributing weight across a complex living framework. The exoskeleton, by contrast, is dead tissue on the outside, a constant, crushing commitment of inert mass. Consider the physical act of movement. Every step taken by the arthropleura was a victory against the gravitational forces acting upon its heavy armor. The muscles, though supercharged by the high oxygen air, had to expend a substantial portion of their energy simply supporting and mobilizing the vast, articulated shell, leaving less energy for foraging or escaping. The joints between the segments of the exoskeleton had to be incredibly robust, yet flexible enough to allow for locomotion, a difficult engineering feat in itself. This inherent mechanical inefficiency meant that giants were likely slower and less agile on land than a large vertebrate would be. This is why, in general, the largest known carboniferous arthropods, like the arthropleura, were terrestrial crawlers rather than jumpers or fast runners. Their size was maximized along the ground, where the earth itself provided some support for the weight. For the flying giants, like the meganeura, the weight of the thoracic armor housing the colossal flight muscles was an even more critical constraint. They dedicated a massive percentage of their overall body mass and metabolic output just to the weight of the hardened shell and the powerful muscles attached to it. While the dense air aided the lift, the exoskeleton acted as a continuous anchor, making their existence a constant, high-energy struggle against gravity. Furthermore, the external skeleton imposed a severe limitation on growth. To grow larger, an arthropod must shed its entire shell, the vulnerable process of molting we will discuss later. For a giant arthropod, the amount of energy and the sheer quantity of material required to form a new, larger shell was astronomical. The new shell had to be formed in a state of deep metabolic stress and then rapidly hardened while the creature was at its most vulnerable. This process was a massive energy expenditure, making sustained, continuous growth incredibly costly. The sheer volume of material needed for a new exoskeleton at 6 feet long meant that the window for growth likely closed relatively quickly, ensuring that the true maximum sizes were achieved by only a fortunate few who could survive the numerous challenging molting cycles. In the end, the exoskeleton's burden meant the giants lived in a world defined by the absolute maximum capacity of their fuel source. The high oxygen air had to work double duty, not only overcoming the diffusion limit, but also constantly fighting the dead, structural weight of their own magnificent armor. They were strong, but their strength was often used simply to support themselves. The giants were magnificent shells of life, but their design placed an unyielding tax on their metabolism. And when the planetary oxygen tax diminished, the weight of their own armor, once a symbol of their size, would become one of the many factors that pulled them back down to Earth. As we conclude our examination of the giants' physical constraints, we must place them back into their living context, a world defined by the silent, relentless pressure of evolutionary competition and predation. The Carboniferous was not a tranquil garden. It was an environment where size, once unlocked by abundant oxygen, became the necessary currency for survival. This was the earliest terrestrial arms race. The gigantism of the arthropods was not merely a passive result of available fuel. It was an active response to the question, how can I survive and how can I eat? In an ecosystem where the respiratory limits were temporarily pushed outward, the default evolutionary strategy became simple: grow larger. For the terrestrial giants, like the colossal millipede arthropleura, reaching lengths of 6 to 8 feet, the pressure was often about deterrence. While its diet is believed to have been largely herbivorous, feeding on decaying plant matter or spores. Its massive, segmented body and thick, rigid armor served as an imposing obstacle to any potential predator. Imagine an early amphibian, a clumsy tetrapod confined to the water's edge. A giant creature lumbering through the damp foliage presented a target simply too large, too armored, and too difficult to subdue without specialized weaponry. Size became a physical declaration of unprofitability to a predator. The cost of attacking and dismantling the massive exoskeleton outweighed the caloric reward. However, the pressure to grow larger was most intense among the predators themselves. The meganeura, with its 2-foot wingspan, was the apex aerial hunter, dominating the rich oxygen skies. Its prey consisted of smaller, early-winged insects and perhaps other arthropod flyers. To maintain its dominance, the meganeura had to outmatch its contemporaries, which were also benefiting from the high oxygen. If a competing dragonfly species evolved a wingspan of 18 inches, the evolutionary trajectory for the successful predator was clear. A 24-inch wingspan provided the speed and reach necessary to maintain the hunting edge. This constant escalation of size ensured that no aerial niche remained small for long. This dynamic created an unstable equilibrium. The arms race, increased size in predators, forced increased size or better defense in prey. Physiological limit. All participants were pushing against the absolute, finite physical limits of the tracheal system and the exoskeleton's weight burden. The Carboniferous was therefore a rare moment in Earth's history where the invertebrates held the top predatory roles. The slow, evolving tetrapods had not yet fully differentiated into fast, efficient land hunters. This absence of highly advanced vertebrate competition allowed the arthropod giants to thrive. They faced challenges from their own kind, but not from the streamlined, warm-blooded hunters that would appear hundreds of millions of years later. For example, the presence of other large arthropod predators, such as colossal spiders or massive scorpions, required defensive size even for herbivores. The arthropleura's armor was a necessity, not a luxury. Its sheer length provided a multi-segmented target, ensuring that a localized injury would not be immediately fatal. In this world, being big was the equivalent of being safe. Yet this reliance on size carried a profound ecological cost. Large organisms require immense amounts of food and territory. The giants were ecologically expensive to maintain. Their population numbers were naturally low, meaning that the survival of their lineage was highly dependent on the stability of their vast food chains. A modern ecosystem has hundreds of species of small insects, filling diverse roles. The Carboniferous, by comparison, featured fewer, larger species, each consuming massive resources. This lack of ecological redundancy meant that when the environment finally failed, the collapse of these megafauna would be swift and total. There were no small, generalist populations of the giants ready to adapt and shrink. The evolutionary pressure in the Carboniferous was a one-way street leading toward the largest possible size. It was a strategy perfectly suited for a stable, oxygen-rich world, but tragically flawed for an era of sudden, global change. The early arms race was ultimately decided not by the hunters or the hunted, but by the atmosphere itself. When the Earth's engine began to reverse, removing the physiological cheat code, the selective pressure to be large instantly inverted. The same weight and metabolic demands that provided temporary supremacy became an unbearable liability. The colossal, beautiful shells of the Carboniferous giants represent the ultimate proof that sometimes the greatest evolutionary success is simply to be small enough to hide and cheap enough to run. We now transition from the rich, humid tranquility of the Carboniferous into the vast, unfolding change of the Permian period. This epoch, spanning roughly 299 to 252 million years ago, marks a critical turning point in Earth's history, the moment the planetary engine shifted, slowly and inexorably replacing the world of boundless swamps with a world of sweeping, arid continental interiors. This transition fundamentally challenged the existence of the giant insects, demanding an adaptation their physiology was ill-prepared to give. The driving force behind this massive environmental transformation was one of the most significant geological events in the planet's history, the formation of Pangaea. Imagine the Earth's tectonic plates, the vast, fragmented pieces of the crust, slowly grinding, colliding, and ultimately fusing together. Over millions of years, the continental landmasses converged, creating a single, enormous supercontinent. This vast landmass stretched from pole to pole, radically altering global ocean currents and, most importantly, weather patterns. The profound size and shape of Pangaea had immediate and devastating consequences for the climate, the creation of a vast continental effect. In our modern, fragmented world, most land is close to the ocean, which acts as a global thermostat, moderating temperatures and delivering consistent moisture. Pangaea, however, created continental interiors thousands of miles away from any coast. The immense mountain ranges formed by the collision of continents acted as insurmountable barriers, blocking moisture-laden air from penetrating the interior. As a result, the once ubiquitous humid climate of the Carboniferous, the moist, tropical environment essential for the giant insects, was squeezed into narrow coastal belts. The vast central regions of Pangaea transformed into colossal, unforgiving deserts. This massive aridification was a physiological catastrophe for the giants. The giant insects, particularly those that flew, required immense amounts of internal moisture to maintain their metabolic processes. The tracheal system, while superb at delivering oxygen, is notoriously inefficient at retaining water. Every spiracle opening, every breath taken to fuel the massive flight muscles, released vital moisture into the atmosphere. In the damp, nearly saturated air of the Carboniferous swamp, this water loss was easily managed. In the Permian deserts, however, the air was hot and dry. The same respiratory system that allowed the giants to be large now became a profound liability, turning every breath into a slow, dehydrating expenditure. The largest insects, with their immense surface area and vast need for oxygen, had the highest moisture demands and the fastest water loss. Simultaneously, the changing climate triggered a dramatic shift in global flora. The low-lying, water-dependent swamp plants that fueled the Carboniferous, the lepidodendron and ferns, were replaced by hardy, drought-resistant species like the gymnosperms, early conifers, cycads, and seed ferns. These new plants were fundamentally different. Their seeds allowed them to reproduce without constant standing water, and their tough, woody structures were far less palatable and nutritious for many of the herbivorous giants. The vast forests of coal began to shrink, fragment, and retreat, replaced by sparser, hardier vegetation. The engine that produced the high oxygen air began to sputter as the global carbon sink diminished. Less carbon was buried, and the delicate equilibrium that maintained 35% oxygen began its long, slow decline. The Permian shift was a period of increasing pressure, a prolonged, silent siege on the giants' magnificent design. Their scale, once an advantage in an unchallenged habitat, became a metabolic and hydration anchor in a world that was demanding efficiency and small, watertight resilience. The change was not immediate, but insidious. Over the expanse of millions of years, the supercontinent's formation sealed the fate of the moist, dark world. The giants who survived had to find refuge in the shrinking coastal margins or evolve profound changes to minimize water loss, a difficult task when your existence is built on maximizing air intake. This shift from global humidity to continental aridity marked the first great selective filter of the giant insect. It set the stage for the true catastrophe to come, proving that the breath of giants could only persist so long as the ancient Earth remained fragmented and damp. we have observed the colossal forces of Pangaea that destroyed the humid, swamp-bound world of the Carboniferous. As the megacontinent grew, the life that survived had to make an unprecedented choice: adapt or perish. This necessity drove a significant portion of the giant arthropods to fully commit to the great terrestrial invasion, moving definitively beyond the coastal swamps and into the drier, more varied inland environments. The term invasion here refers not to a sudden charge, but to a long, slow evolutionary process. For arthropods, the initial leap from the water, their ancestral home, to the land was the first great challenge. Now, in the face of widespread aridification, the second, more subtle challenge arose: the retreat from the moisture-dependent margins. The giants that successfully made this second transition developed remarkable, albeit temporary, physiological workarounds to combat the relentless Permian drought. One critical adaptation involved the spiracles, the entry points for the tracheal system. In the damp Carboniferous air, these openings could afford to be relatively large and open to maximize oxygen intake. But in the Permian heat, every open spiracle meant massive water loss. The giants that survived in the drier environments likely evolved sophisticated closing mechanisms for their spiracles. Imagine tiny, precise valves and filters designed to minimize air exchange, except when absolutely necessary, often during periods of rest or cool evening temperatures. This careful control allowed them to conserve the precious internal moisture that was constantly being wicked away by the arid air. This adaptation came with a metabolic trade-off: reduced activity. To breathe less often and conserve water meant they could not sustain the continuous high-energy activity required of their ancestors. The life of a terrestrial giant became more about patience and efficiency than raw power. Another key to the inland migration was dietary flexibility. The Carboniferous giants were often highly specialized feeders, relying on the abundant, soft tissues of the swamp plants. As the flora shifted to tougher, drought-resistant gymnosperms, plants with thicker cuticles, protective resins, and tougher internal structures, the surviving giant herbivores, like the larger relatives of the millipedes, had to develop immensely powerful mandibles and highly resilient digestive systems. Their sheer size provided the necessary leverage and muscle mass to process this tougher, lower-quality food source. The ability to chew and digest the coarse, dry leaves of the early conifers allowed them to colonize areas where the lush, soft swamp vegetation could no longer survive. Furthermore, the Permian land invasion forced the giants to master burrowing and microclimates. A creature as large as an arthropleura descendant couldn't survive the midday heat of a continental desert simply by standing still. To escape the extreme solar radiation and the dehydrating winds, they relied on their scale to efficiently create burrows and deep shelters. Their powerful, armored bodies were used as tunneling machines, allowing them to dig deep into the substrate where the temperature remained stable and the humidity level was significantly higher. These deep refuges allowed the giants to survive the harsh Permian days, emerging only during the cooler, damper nights to feed. In this way, they didn't conquer the desert. They outweighted it, exploiting the subtle differences between the deadly surface environment and the survivable subsurface. For the aerial giants, the survivors had to shrink. The largest of the meganeura, whose massive size was entirely dedicated to aerial dominance in thick air, mostly vanished. Their smaller, more resilient descendants that survived the Permian drought were those who could manage flight with less oxygen, and critically, those whose smaller surface area allowed them to lose less water. Miniaturization became a sudden, necessary adaptation for survival in the air. This era of adaptation highlights a critical evolutionary principle: resilience over specialization. The creatures that clung rigidly to the old, large, water-dependent blueprint were lost as the swamps dried. The giants that survived, even temporarily, were those who could utilize their size to solve the new problems of heat and desiccation by digging, by conserving and by eating the tough new food sources. The retreat from the sea was a testament to the incredible toughness of the arthropod lineage, showing their ability to adapt to a world that was actively trying to kill them. They successfully navigated the vast new continents, but their success was tenuous. They were now living on the frayed edges of their own physiological design, waiting for the next, inevitable change that would push them past the point of no return. We have explored the grand scale of the giant arthropods, creatures whose very existence was a triumph of adaptation over physical law, yet their magnificent design concealed a catastrophic weakness, an essential, unavoidable process that represented their greatest physiological risk, molting or ecdysis. For the colossal insects of the Permian, this necessary act of growth was a period of extreme vulnerability, a deadly protracted gamble against gravity, time, and the subtle shift of their environment. Molting is the singular mechanism by which all arthropods grow, confined by their external skeletons, their exoskeletons. They must periodically shed the rigid, non-living armor to expand their soft bodies beneath before hardening a new, larger shell. For the giants, this biological necessity was a monumental engineering challenge that exposed them to fatal risk. Imagine a 6-foot-long arthropleura preparing to molt. The process begins internally with the separation of the old cuticle from the new, softer layer forming beneath. This is followed by the insect attempting to literally walk out of its own skin. The physical mechanics of this process for such a massive creature are staggering. The immense body mass, already straining against gravity, must now be supported entirely by internal fluid pressure, the equivalent of an inflatable skeleton. The old rigid shell acts as the necessary leverage point to pull the soft body out, often against the immense pull of gravity. Any miscalculation, any slip, or any structural failure during this arduous, hours-long maneuver could be immediately fatal. The primary risk during ecdysis is mechanical failure and deformation. If the weight of the massive body causes the delicate, soft new exoskeleton to buckle or deform before it has a chance to fully inflate and harden, the creature is effectively crippled. A deformed leg joint or a crushed thoracic segment meant certain death in a world where survival demanded perfect physical form. This difficulty grew exponentially with size. The larger the arthropod, the greater the gravitational forces acting on its unsupported mass. Even if the mechanical challenge was overcome, the giant was left in an extended, agonizing state of vulnerability. For a small modern insect, the hardening process, the time during which the soft, tendril shell is susceptible to attack, is relatively brief. For the Permian giants, generating and hardening a new, thick, multi-segmented shell the size of a small car required an enormous commitment of time and energy. This meant the giant insect was immobile and defenseless for an extended period, days, perhaps even a full week, a soft, massive, highly nutritious target waiting for any small predator to discover its location. Every rustle in the surrounding vegetation, every shadow cast by a passing animal would have represented a moment of existential terror. This is why the successful molting process likely required a specialized, safe microclimate, a hidden crevice, a sheltered bank, or a dense patch of foliage. A secure sanctuary the Permian aridification made increasingly scarce. Furthermore, molting was an intense period of respiratory crisis. During the hours-long exertion of shedding the old armor, the spiracles were often partially or fully restricted. The new tracheal linings were being shed along with the old shell, creating a profound temporary disruption in the passive oxygen supply. The massive flight muscles, or the colossal leg muscles, were starved for oxygen at the very moment they required maximum exertion to pull free. In the high oxygen air of the early Carboniferous, This respiratory debt was manageable. The ambient air could force enough oxygen into the system even through restricted paths. However, as the atmosphere began its slow, inevitable decline in the Permian, the margin for error during molting rapidly vanished. A drop from 35% to 28% oxygen meant the effort of molting, once merely difficult, became lethally hypoxic, oxygen-starved. The giant could die not from a predator, but from simple exhaustion and suffocation while trying to pull its own body from the old shell. The mystery of molting is that it demonstrates the profound biological cost of the arthropod body plan at extreme size. It was a beautiful but fundamentally restrictive design, making the process of growth a recurring, high-stakes crisis. For the Permian giants, the struggle to grow was ultimately a factor in their demise. The difficulty of molting restricted the frequency of their growth cycles and limited the maximum size achievable, ensuring that they could not outgrow the environmental changes fast enough. Their vulnerability during ecdysis meant that any environmental stressor, whether a subtle drop in humidity or a slight decrease in oxygen, had an immediate, lethal impact on their ability to perpetuate their colossal lineage. The sheer mass of the giant Carboniferous arthropods, such as the 3-foot-long, millipede-like arthropleura or the massive dragonflies like meganeura, pushed the biomechanical limits of the exoskeleton to its absolute breaking point. While the high oxygen atmosphere of the time allowed for large respiratory systems, gravity imposed a far stricter constraint on their locomotion, a challenge that ultimately contributes to the mystery of their disappearance. The arthropod body plan relies on an external skeleton, exoskeleton, or cuticle made of chitin and protein. This design is highly efficient for small creatures, offering protection, muscle attachment points, and structural support. However, its efficiency drops exponentially as size increases due to two critical, interlocking principles: the square-cube law and joint stress. The square-cube law dictates that as an object grows larger, its volume, and thus its mass or weight, increases by the cube of its dimensions, while its cross-sectional area, and thus the strength of its supporting limbs, increases only by the square of its dimensions. Weight versus strength. A giant insect twice as long as a modern one would be 23.8 times heavier, but its legs would only be 22.4 times stronger. This rapidly diminishing ratio of strength to weight meant that for the very largest giants, an increasing proportion of their muscle mass had to be dedicated simply to supporting the exoskeleton, leaving less energy for movement, foraging, and escape. The cost of armor. The exoskeleton itself is heavy. For arthropleura to support its colossal segmented body off the ground, its cuticle had to be significantly thicker and heavier than any modern insects. This self-imposed burden meant that the creature was constantly fighting its own structure, creating an inefficient body plan that demanded massive energetic input just to maintain a resting posture. The locomotion of an arthropod is defined by its jointed limbs, which rely on muscles operating internal to the exoskeleton to move rigid segments. This joint system is highly vulnerable to compressive stress under heavy load. The problem of torsion and buckling, a vertebrate leg, composed of internal bone, is designed to handle compressive loads, pushing forces vertically. An arthropod leg, however, is a hollow tube. When a heavy, jointed limb is fully extended to bear weight, the points where the segments meet become areas of immense torsional stress and buckling risk. For a creature the size of a small car, like arthropleura, a misstep or a slip could result in a catastrophic joint failure, crushing the soft tissues within the leg. Leverage inefficiency. Arthropod muscles pull from inside a rigid shell. This is an efficient lever system for small, lightweight limbs. However, for a massive limb, the necessary muscle size and attachment points required to generate enough torque, rotational force, to lift and swing a heavy, chitinous leg quickly become mechanically impractical. The muscles would need to be prohibitively large and bulky, adding yet more weight to the body. This is a key reason giant insects would have moved relatively slowly compared to their small modern counterparts. The physical constraints imposed by gravity directly affected the giant insects' metabolic rates and behavioral limits. Treadmill analogy. Imagine running on a treadmill. For a small insect, the energy cost of running is low. For a massive insect, the cost of lifting and moving its heavy body against gravity becomes the dominant energy expenditure. This high metabolic cost made them less energy efficient than the emerging, more structurally sound vertebrate forms. Safety and habitat. The giants' sheer weight meant they had to prioritize stable, flat surfaces. They likely avoided complex three-dimensional movements and could not risk navigating uneven terrain, as a fall or loss of footing could be disabling or fatal. This restricted their habitat, concentrating them in the swampy, flat lowlands, the same areas that were first affected by the Permian climate shifts. In the Carboniferous, the high oxygen air compensated for the inefficient respiratory system, allowing the creatures to support the heavy, structurally constrained body plan. However, as the atmosphere began to thin and the climate destabilized in the Permian period, the gravitational constraint was suddenly amplified. Lower O2 meant less energy could be supplied to the muscles, reducing the power available to lift the heavy body. Structural inefficiency. The heavy exoskeleton, necessary for structural integrity, now had to be lifted by muscles running on a leaner oxygen diet. The combination proved fatal. The biomechanically inefficient giant body plan, already at its gravitational limit, could not compete with the emerging vertebrate body plan, which utilizes internal skeletons and more efficient circulatory systems to scale effortlessly against gravity. Ultimately, the rigid, heavy, and joint-vulnerable design of the giant arthropods was simply too costly to maintain once the world's perfect, high-oxygen environment began to falter, sealing the fate of the walking behemoths. We have tracked the slow geological inevitability of the Permian shift, the formation of Pangaea, and the resulting aridification of the continental interior. Yet, long before the final catastrophic extinction pulse, the world presented the giant insects with a more subtle, equally profound threat: climate volatility. We call this the flicker effect, a period of increasing, unpredictable extremes that began to break the metabolic resilience of the giants. The Carboniferous was defined by stability, high oxygen, high humidity, and consistent temperatures. The early Permian, dominated by the supercontinent, introduced a broad, persistent dryness. The late Permian, however, introduced erraticism. The world began to flicker, alternating between harsh, cold snaps and blistering, intense heat waves. This volatility was driven by several interconnected factors related to the geography of Pangaea. With the land mass concentrated into a single, massive body, the moderating effect of the oceans was drastically diminished. Large continents heat up quickly in the summer and cool down quickly in the winter. Imagine the interior of Pangaea. Intense summers. Without ocean currents to cool the vast landmass, continental interior temperatures would soar far higher than today's tropics, creating prolonged, dehydrating heat waves, brutal winters. Conversely, in the higher latitudes and during winter months, the interior would experience severe freezes, true continental winters that plunged temperatures far below those tolerable for giant, cold-blooded, ectothermic creatures. For the colossal arthropods, whose internal body temperature is dictated largely by their environment, this thermal oscillation was devastating. They were metabolically designed for a narrow band of tropical humidity. A massive insect has a low surface area to volume ratio. While this is beneficial for retaining heat in a stable environment, it becomes a severe disadvantage under thermal extremes. They were slow to warm up, but crucially, they were also slow to cool down. During sudden heat waves, the massive body could rapidly reach lethal temperatures, and the giant lacked the internal mechanisms, like sweating or rapid panting, to shed that heat fast enough. They would essentially overheat from the inside out, unable to sustain activity or even life. The flicker effect made the giant's respiratory problem worse. As temperatures soared, the giant insect's metabolic rate, its internal oxygen demand, also increased dramatically. Imagine a giant, thick-bodied insect attempting to survive a 120-degree Fahrenheit day. Its cells are screaming for oxygen to run the chemical processes necessary to cope with the heat stress. But the oxygen levels, already declining from the Carboniferous peak due to the slowing carbon burial, were insufficient to meet this sudden, extreme demand. The temperature, therefore, directly exacerbated the oxygen constraint. The combination meant that the giants were trapped. They couldn't move or seek shelter without overheating, and demanding more oxygen than the thinning air could provide. The unstable climate also manifested in highly erratic weather patterns. The supercontinent's complex weather systems meant that rain was not only scarce in the interior, but also unpredictable. Periods of long, scorching megadroughts would suddenly be punctuated by short, violent periods of torrential rain and flash flooding. For the giant insects that relied on burrowing and stability, this unpredictability was lethal. Droughts. These intensified the water loss problem associated with the tracheal system, killing off food sources and forcing metabolic shutdown. Flash flooding. Sudden, intense rain could quickly fill the deep, crucial burrows that protected the giants from the heat, drowning the immobile, massive arthropods trapped within their own shelters. The flicker effect turned the environment into a relentless, low-grade torture test. The giants were constantly forced to commit vast amounts of energy to simply regulate their body temperature and conserve water, leaving little in reserve for growth, reproduction, or defense. This extended period of instability served as a slow but powerful selective filter. It favored the smaller, more agile arthropods, those with a higher surface area to volume ratio who could dissipate heat quickly and who could survive on fewer resources. These smaller insects were simply cheaper to run and easier to hide. The giants, the most specialized creatures on the planet, needed absolute consistency to thrive. The unpredictable fluctuations of the late Permian climate, the alternating cold, heat, drought, and deluge wore down their reserves, weakened their populations, and left them profoundly stressed. They were not yet dead, but they were exhausted, brittle, and poised on the brink. The flicker effect was the long, drawn-out preparation for the final act of planetary violence that would soon follow. We turn our attention now to a silent, yet revolutionary force that fundamentally reshaped the Permian landscape, the evolution of the seed. This tiny, armored package of life marked a permanent shift in global flora, directly influencing the decline of the giant insects by altering their food supply and dismantling the ancient ecosystem they relied upon. The Carboniferous swamp forests were dominated by plants that reproduced using spores, minuscule, dust-like reproductive units that required constant, ubiquitous moisture to germinate and grow. This dependence on standing water meant that the forests were geographically locked into the humid, coastal regions. The plants themselves were often characterized by soft, succulent tissues, easily digestible by the early giant herbivores. The shift that began in the Permian was the rise of the gymnosperms, literally meaning naked seeds. These included the ancestors of modern conifers, cycads and ginkgos. The seed was the ultimate evolutionary innovation for an arid world, granting these plants freedom from the water's edge. Imagine the seed as a portable nursery. It contains the embryo, food reserves, and a tough protective coat, allowing the plant to wait out periods of extreme drought and cold before germinating. This profound adaptation allowed seed-bearing plants to rapidly colonize the vast, arid continental interiors created by Pangaea. The ecological impact, a twofold crisis. Spread of the seed-bearing plants created a twofold crisis for the giant arthropods: habitat destruction and fragmentation. As the climate grew drier, the spore-bearing swamp forests, the original engine of high oxygen and the giants' primary habitat, retreated into ever smaller refuges. In their place, vast, drier forests of conifers and cycads spread. For the giant herbivores like arthropleura and the massive grazing insects, their world became fragmented. They were forced to traverse immense, dry, exposed distances between patches of suitable food. This increased metabolic stress and water loss, while simultaneously making them vulnerable to the thermal extremes of the open landscape. Their enormous bodies, once hidden and protected by the dense, multi-layered canopy of the swamp, were now exposed to the unforgiving Permian sun. Altered nutritional quality. The chemical composition of the new flora was a metabolic nightmare for the giants. To survive the dry, harsh conditions, the gymnosperms evolved protective measures. Tougher structure. Lignin content increased dramatically, making the leaves and wood tough, fibrous, and difficult for the arthropod's simple digestive system to process. Chemical defenses, conifers, in particular, produced resins, terpenes, and toxic secondary compounds, natural, chemical deterrents designed to discourage grazing. The colossal herbivores, designed to process large volumes of soft, nutritious Carboniferous ferns, were now faced with a food source that was less digestible and in some cases actively poisonous. Their already taxed metabolism, struggling with lower oxygen levels, had to work exponentially harder to extract sufficient energy from this low-grade, high-defense vegetation. Imagine having to eat twice as much, chew 10 times harder, and extract half the energy, all while suffering from mild internal toxicity. The energy budget of the giant was already strained by the burden of its own size. This shift in food quality pushed them into a perpetual caloric deficit. The speed of change. This floral turnover was not a slow evolution like the growth of Pangaea. It was relatively rapid from a geological perspective, driven by the immediate selective advantage of the seed. The dominance of the gymnosperms effectively decoupled the land-based flora from the abundant water supply, permanently changing the dynamics of the global ecosystem. The simple fact is that the ancient giants were too specialized for the soft tissue world. They lacked the flexibility, the evolutionary time, and the metabolic capacity to evolve the necessary detoxification pathways and gut microbes required to thrive on the tough, chemical-laden diet of the new Permian forests. The tiny seed, a silent, brilliant achievement of plant evolution, thus became an indirect, powerful contributor to the extinction of the giants. It dried up their habitat, fragmented their populations, and replaced their high-octane fuel with a low-grade, poisonous substitute. It was a crisis initiated at the base of the food chain, illustrating that the survival of the largest consumers is always governed by the quiet resilience of the smallest producers. We have catalogued the environmental pressures, the heat, the drought, the tougher food, that besieged the giant arthropods of the Permian. Now we must examine the internal price of their size, a cost measured in the continuous, unforgiving expense of energy. This is the chapter of the metabolic demands, where we realize that their colossal size, once a triumph, became an immense, inefficient furnace that required constant fueling in a world running low on supplies. Every living organism requires a baseline level of energy simply to maintain life, to repair tissues, circulate fluids, and sustain nerve function. This is the resting metabolic rate. For the colossal arthropods, this rate was astronomical compared to smaller modern insects. Due to the square-cube law we have previously discussed, the giant's mass increased by the cube, meaning its volume, the the sheer amount of living tissue that had to be supplied and maintained was immense. The thick, chitinous exoskeleton alone, which made them structurally viable, represented a massive commitment of dead weight that required disproportionate muscle power just to manage and move. The inefficiency of scale, the energy demands were not just high, they were inefficient. Unlike vertebrates, which evolved high-efficiency endothermic, warm-blooded systems to process food and maintain a constant, optimal temperature, the giants were ectotherms, cold-blooded. Their body temperature fluctuated with the environment. While being ectothermic is metabolically cheap when resting in a stable, warm climate like the early Carboniferous, it becomes ruinously expensive when activity is required. The giants had to use immense bursts of energy, often fueled by the high oxygen, to warm their colossal bodies enough to perform powerful feats like aerial pursuit or burrowing. The problem of maintaining this massive, demanding system was twofold: locomotion and maintenance. As established, the segmented legs and external armor created profound structural inefficiency. Each movement, each step of the arthropleura, or each pump of the meganeura's flight muscles had to overcome not only the force of gravity, but also the mechanical constraints of the heavy shell. This meant that the cost per unit of distance traveled was exponentially higher for the giants than for a smaller, lighter insect. They were essentially running a massive, heavy machine on increasingly low-grade fuel. The nutritional deficit. This high energy demand collided catastrophically with the changing food supply. As the soft, nutritious Carboniferous ferns were replaced by the tough, chemically defended Permian gymnosperms, the giants had to eat exponentially more to meet the same caloric needs. Imagine the metabolic demand as a daily budget. Carboniferous budget. Fuel is high-octane, nutritious ferns. Oxygen is superabundant. The budget is met easily, allowing surplus for massive growth. Permian. Budget fuel is low-grade, tough conifers. Oxygen is declining. The budget remains huge, but the income has been slashed. The giants were forced into a perpetual state of caloric deficit, a slow, internal starvation. They simply couldn't eat enough of the new food quickly enough to sustain their massive, high-maintenance bodies. This constant energy debt led to slower growth, reduced reproductive success, and chronic physical stress. The oxygen demand collapse, perhaps the most critical collision, occurred when the metabolic demands met the oxygen decline. When an animal exerts itself, when it runs, flies, or fights, its metabolic rate, and thus its oxygen requirement, skyrockets. For the meganeura, a sudden, high-speed chase would require instantaneous, massive oxygen delivery to the flight muscles. As the atmospheric oxygen dropped in the Permian, the absolute amount of oxygen available to diffuse into the colossal muscle mass was critically reduced. The muscles were demanding 10 units of oxygen to function, but the thinning air could only physically deliver 5 units. The giant was forced to operate in a constant state of oxygen debt, restricting its speed, duration of flight, and overall hunting success. The cost of being large was now an outright impossibility in high-stress situations. The metabolic demands thus served as the constant, internal clock ticking down to the giant's doom. Their body plan, designed for a world of energy surplus, was structurally and physiologically unviable in a world demanding metabolic frugality. The successful insects of the future would be those who minimize this internal cost, small, light, and hyper-efficient. The giants, magnificent as they were simply too expensive for the changing planetary economy, making their ultimate demise not just a climatic tragedy, but a metabolic certainty. We now arrive at the moment of ultimate catastrophe. The slow, relentless pressures of the Permian shift, the declining oxygen, the rising heat, the structural burdens, had already weakened the giants, but they had not yet vanished. That final, lethal blow would be delivered not by climate change, but by a sudden, unimaginable outburst of planetary violence, the eruption of the Siberian Traps. This event, occurring roughly 252 million years ago, marks the beginning of the Permian-Triassic extinction event, often dubbed the Great Dying. It was the most profound biological crisis in Earth's history, and its trigger was a volcanic event of a scale we can barely comprehend. Imagine a volcano, not as a single conical mountain, but as a vast, continental-scale fissure, miles deep, relentlessly bleeding magma onto the surface of the Earth. The Siberian Traps were a large igneous province, LEP, a geological term for an immense area where enormous volumes of lava flowed rapidly and repeatedly over a period that may have lasted less than 2 million years, an instant in geological time. These eruptions poured out an estimated 2 to 3 million cubic kilometers of basaltic lava, covering an area of nearly 7 million square kilometers in modern-day Siberia. This vast expanse of volcanic rock, stacked miles high, represents the sheer, terrifying volume of material released from Earth's deep mantle. The mechanism of the Siberian Traps was not explosive like Vesuvius or Mount St. Helens. It was predominantly effusive, meaning the lava flowed out across the landscape in vast, dark, silent sheets, trapping and burning everything in its path. But the truly catastrophic effect was not the lava itself, but what the heat released from the subsurface. The rising magma plume did not just breach the surface. As it pushed upward through the Earth's crust, it invaded and heated immense underground deposits of coal, oil shales, and salt formations. Imagine a geological oven baking hundreds of millions of years of stored carboniferous material. This deep, intense heating achieved 3 lethal results that sealed the fate of the atmosphere and, consequently, the giants. Massive CO2 injection. The baking of coal and organic-rich shales released staggering quantities of carbon dioxide, CO2, directly into the atmosphere, rapidly and violently reversing the slow carbon sequestration that had defined the Carboniferous. This reversed the long-term trend of falling oxygen and instantly created a super greenhouse effect. Methane hydrate release. The heat destabilized vast reserves of methane hydrates, frozen methane stored in the ocean floor and in permafrost. Methane is a greenhouse gas, many times more potent than CO2. Its sudden, immense release created a positive feedback loop, dramatically accelerating the global temperature rise in a runaway fashion. Sulfur and halogen compounds. The eruptions also released tremendous volumes of sulfur dioxide, SO2, and chlorine-fluorine compounds. These created widespread severe acid rain that destroyed plant life on land and acidified the surface waters of the ocean. The cumulative effect was the destruction of the atmospheric balance. Within a very short time, perhaps as little as a few thousand years, global temperatures soared by an estimated 5 to 8 degrees Celsius. The high oxygen, cool, stable world the giant insects depended on was violently replaced by a hot, acid-soaked, suffocating inferno. The Siberian Traps were the ultimate force multiplier. They took the existing weaknesses of the giants, their high metabolic demand, their struggle with heat, and their reliance on a specific oxygen partial pressure, and amplified them into immediate, total extinction drivers. The air itself, which had been the giants' great enabler, was about to turn into their prison. The volcanic genesis in Siberia was a terrifying reminder that the Earth, in its deepest workings, does not differentiate between life and rock. It simply changes, and sometimes that change is swift, catastrophic, and final. The geological violence unleashed by the Siberian Traps was only the first act. The truly catastrophic consequences for the giants came with the second, the unprecedented contamination of the atmosphere and oceans. This was the moment the ancient world's hidden geological deposits detonated. creating the carbon bomb that pushed Earth's climate past the point of no return. As the magma plumes of the Siberian traps continued to relentlessly ooze forth, their superheating of the crust released stored materials that had been locked away for hundreds of millions of years. This included vast reservoirs of coal, oil shales, and carbonates, carbon locked in sedimentary rocks. The resulting outgassing was a monumental double dose of poison for the giant insects, an overwhelming surge of carbon dioxide, CO2, and a lethal cloud of sulfur dioxide, SO2. The CO2 surge, the runaway greenhouse, the sheer volume of carbon dioxide released dwarfed any natural or industrial emissions known since. This massive, sudden injection of CO2 into the atmosphere acted as a hyper-efficient greenhouse gas, trapping the sun's heat and triggering a rapid, global temperature increase. Within a relatively brief geological span, thousands to tens of thousands of years, global average temperatures climbed dramatically, leading to the lethal thermal extremes we discussed earlier. For the ectothermic giants designed for the stable, moderate temperatures of the Carboniferous, this rapid heating was instantly debilitating. Their massive bodies, slow to cool, quickly exceeded their thermal tolerance thresholds. But the CO2 crisis had an even darker consequence: ocean acidification. The atmosphere and ocean exchange gases constantly. As atmospheric CO2 levels skyrocketed, the oceans absorbed an enormous amount of the gas. When CO2 dissolves in water, it forms carbonic acid. This process rapidly increased the acidity of the surface waters, dismantling the ocean's food chain from the bottom up. This is a critical link to the terrestrial giants. The collapse of marine life, particularly the calcium-shelled organisms, disrupted the global carbon cycle and led to widespread ocean anoxia, oxygen depletion, ultimately feeding back into the atmospheric crisis and further destabilizing the entire planetary system. The SO2 and halogen cloud, acid rain, and toxic air compounding. The CO2 crisis was the injection of vast quantities of sulfur dioxide, SO2, and various halogen compounds, chlorine and fluorine, from the volcanic vents. Sulfur dioxide, upon mixing with atmospheric water vapor, forms highly corrosive sulfuric acid. This led to a global regime of severe acid rain. Imagine rain so corrosive that it systematically destroyed the land-based flora. For the giant herbivores, this was a final blow to their already compromised food supply. The new gymnosperms, though hardy, were not immune. The extensive destruction of vegetation destabilized soil, triggered massive erosion, and further contributed to the mass starvation of the terrestrial ecosystem. The world turned sickly and bare. Furthermore, the release of these toxic compounds meant that the air itself, which the giants required in such immense volumes, was now actively poisonous. The combination of the two gas crises created an environmental trap. Too hot, the CO2 made the environment thermally lethal. Too acidic, the SO2 and its acid rain destroyed the base of the food chain. Too thick and thin, the rapid, erratic changes in atmospheric composition created a metabolic nightmare, combining the pressure of a thinning oxygen supply with the overwhelming presence of toxic gases that inhibited respiration. The carbon bomb did more than just change the climate. It systematically poisoned every reservoir of life, from the deep ocean to the highest reaches of the atmosphere. The giant insects, already strained by their colossal size and high-maintenance physiology, had no capacity to adapt to this instantaneous, multifaceted assault. The world that had been their unique garden had turned against them with terrifying speed and finality, setting the stage for the true physiological killer of the giants, the insidious process of CO2 poisoning, which we will explore next. We have identified the Siberian traps as the source of the carbon bomb, releasing unimaginable quantities of CO2 into the Permian atmosphere. While many discussions focus on the associated decline of oxygen, An increasing body of scientific thought suggests that the final, most direct physiological assassin of the giant insects was not the lack of fuel, but the inability to expel their own waste. This is the phenomenon of hypercapnia, the hidden killer of the giants. To understand this lethal mechanism, we must revisit the fundamental physics of gas exchange within the insect's tracheal system. Respiration involves two vital steps: taking in oxygen, O2, and, equally important, getting rid of the metabolic waste product, carbon dioxide, CO2. Both processes rely on diffusion, the passive movement of gas from high concentration to low concentration. In the case of CO2, the giant insect cells continuously produce this waste gas, creating a high concentration inside the body. This CO2 then diffuses outward through the tracheoles and spiracles into the low concentration atmosphere. This outward-bound diffusion is essential. If the CO2 builds up inside the body, it turns the internal fluids highly acidic, leading to immediate physiological collapse. The catastrophe of the Siberian traps was the rapid, immense increase in atmospheric CO2. While modern air contains about 420 parts per million ppm of CO2, the Permian crisis pushed concentration to levels potentially ranging from 3,000 to over 10,000 ppm of concentration, more than 20 times higher than today. This massive external surge created a lethal atmospheric back pressure against the giant insect's respiratory system. Imagine the high concentration of CO2 inside the insect's body trying to diffuse out. It is now met by an external atmosphere that is already saturated with CO2. The critical concentration gradient, the difference required to drive the gas exchange, was drastically reduced, or even eliminated. The result was a failure to ventilate. The giant insect could no longer effectively exhale. The carbon dioxide that was once passively and efficiently released into the environment began to accumulate rapidly within the giant's tissues. This internal buildup of CO2 is what defines hypercapnia. The immediate biological consequence of hypercapnia is the severe acidification of the hemolymph, the insect's blood, and all internal body fluids. Insects, being ectothermic and lacking the complex buffering systems of vertebrates, are highly sensitive to these changes in pH. As the fluids turned acidic, enzyme malfunction. The essential enzymes that drive metabolism and nerve function began to break down or operate inefficiently. Paralysis and stupor. High CO2 is a known anesthetic and paralytic agent for insects. The giants would have fallen into a state of lethargy, stupor, and eventual paralysis, unable to coordinate their massive bodies or operate the muscles needed for flight or escape. Spiracle closure. In a final, desperate and ultimately counterproductive defense mechanism, some insects naturally respond to high internal CO2 by closing their spiracles to conserve water. In the hypercapnic Permian atmosphere, this response only accelerated the internal buildup of the lethal gas, ensuring a swift, silent death. The beauty of the giant insect's tracheal system was its simplicity and efficiency in an ideal environment. But this simplicity was also its great vulnerability. It provided no mechanism for active expulsion of waste gases against a pressure gradient. The hypercapnia theory posits that the colossal insect populations, already weakened by declining oxygen, rising heat, and poor nutrition, were killed not by a slow choke, but by a rapid, systemic poisoning from their own inability to expel metabolic waste. They were overwhelmed by their own size and by the sudden, toxic saturation of the atmosphere that encased them. This theory provides a crucial explanation for the selectivity of the extinction event. Smaller arthropods having a high surface area-to-volume ratio could still manage to vent enough CO2 across their surface or through shorter tracheal systems to survive the elevated atmospheric concentrations. The giants, with their massive tissue volume and reliance on long-distance diffusion, simply had nowhere for the gas to go. The Siberian traps turned the planet into a giant, silent carbon dioxide chamber, and the largest arthropods were the first to succumb, quietly paralyzed and poisoned by the very atmosphere that once elevated them to greatness. We have tracked the immediate, deadly consequences of the carbon bomb on the giant insects: lethal heat and hypercapnia. Yet, the catastrophic emissions from the Siberian traps triggered a series of destructive chain reactions that propagated through the entire global system, destroying the very foundation of the biosphere, both on land and in the oceans. This was a global ecological collapse fueled by acid rain and the silent spreading of ocean anoxia. As the volcanic vents released immense volumes of sulfur dioxide, SO2, and halogens, chlorine, fluorine, these gases rose into the atmosphere. Upon mixing with water vapor, they formed potent corrosive acids, primarily sulfuric acid and hydrochloric acid. This resulted in a global regime of highly acidic precipitation. Imagine rain not as a life-giving element, but as a slow, systematic destroyer. The consequences for the terrestrial ecosystem, already strained by the drought and temperature extremes, were devastating: defoliation and soil poisoning. The highly acidic rain directly scorched and withered the leaves of the surviving Permian flora, particularly the fragile reproductive organs of plants. This rapid defoliation removed the primary energy source for the entire food web, accelerating the mass starvation of herbivores, including the giants who relied on continuous, massive food consumption. Nutrient stripping. The acid rain dissolved critical nutrients from the soil, washing them away into rivers and streams. This further weakened the already struggling plant life and effectively sterilized vast tracts of land, making recovery impossible in the immediate aftermath. Widespread erosion. With the protective canopy and root systems destroyed by acid and drought, the exposed soil was easily washed away. Massive erosion events choked river systems and dumped enormous loads of sediment and terrestrial toxins into the oceans, triggering the second, even larger crisis beneath the waves. The destruction on land fed directly into the collapse of the marine environment, which experienced the greatest loss of life during the Permian extinction, up to 96% of all species. The key mechanisms were acidification and anoxia. The surging atmospheric CO2 was absorbed by the oceans, triggering rapid ocean acidification. This change in pH was lethal to marine life that relied on calcium carbonate to build their shells and skeletons. Creatures like corals, plankton, and vast numbers of mollusks and brachiopods. These calcareous organisms form the very base of the marine food web. Their massive, sudden die-off triggered the cascade we call ocean anoxia, the catastrophic depletion of oxygen in the water column. Here is how the anoxia spread. Stagnation and warming. The extreme global warming, driven by the CO2 surge, significantly raised ocean temperatures. Warm water holds far less dissolved oxygen than cold water. Furthermore, the temperature increase reduced the density difference between surface and deep waters, preventing the normal vertical circulation patterns, ocean mixing, that deliver oxygen to the deep ocean. The water became stagnant. Nutrient overload and decay. The massive influx of nutrients from the eroded, acid-soaked land combined with the collapse of the surface food chain created an enormous amount of decaying organic matter that sank to the seabed. Bacterial bloom. As this material decayed, bacteria rapidly consumed the remaining oxygen in the deep water. The bottom layer of the ocean became a vast, silent zone of anoxia, a dead zone where oxygen levels dropped to zero, allowing only anaerobic, non-oxygen-breathing bacteria to survive. This anoxia then began to spread upwards, consuming the water column and trapping marine life. The ocean became a suffocating, stratified, toxic brew. Crucially, Some anaerobic bacteria in these deep anoxic zones produce hydrogen sulfide gas, H2S, a potent poison. If the anoxic layers grew large enough, this deadly gas could have potentially bubbled up to the surface and into the atmosphere, creating a final lethal wave of atmospheric toxicity, further compounding the crisis for the terrestrial survivors. The acid rain and ocean anoxia chain reaction demonstrates the interconnected fragility of the biosphere. The fate of the giant insects already sealed by the gases they breathed was guaranteed by the destruction of the world that fed them. The ecological systems they depended on for shade, moisture, and food were utterly dissolved, leaving behind a scarred, silent planet ready for a new, smaller kind of life to begin anew. We have followed the chain of destruction, from the depths of the Siberian crust to the poisoned atmosphere and the suffocating oceans. We now stand at the apex of the crisis, the extinction pulse, the final, devastating period of the Permian-Triassic event, justly remembered as the Great Dying. This was the greatest biological catastrophe in Earth's history, a silent, pervasive sweep that permanently erased the giant insects and nearly ended life itself. Imagine the planet during this final collapse, roughly 252 million years ago. It was not a sudden explosion, but a prolonged, relentless thinning of the tapestry of life, driven by the combination of thermal stress, hypercapnia, and starvation. The interconnected crises we have explored converged into a single, lethal wave. The statistics of this pulse are stark and unparalleled. An estimated 96% of all marine species and 70% of all terrestrial vertebrate species were wiped out. For the invertebrates, including our giant insects, the loss was equally comprehensive. For the magnificent arthropods, the extinction pulse did not come as a single dramatic moment. Their demise was a consequence of the systemic failure of the world that sustained them. Metabolic suffocation. The high atmospheric CO2 concentration made their essential passive tracheal system unviable. Already weakened, the giants succumbed to hypercapnia, their internal fluids turning acidic, leading to paralysis and death. Their immense size, which was once their advantage, ensured they were the first to be metabolically choked by the altered air. Thermal overload. The continuous, intense global warming pushed the ectothermic giants past their thermal limits. Without internal regulation and with massive bodies slow to cool, they literally overheated in the sun-drenched humid air, dying in stupor or in failed attempts to reach vanishing cool, sheltered microclimates. Food web collapse. The acid rain and drought destroyed the Permian forests, the food source for the colossal herbivores like the arthropleura descendants. The marine collapse, driven by ocean anoxia and acidification, similarly annihilated the base of the food web for all coastal and amphibious life. Starvation followed quickly on the heels of poisoning. The giant insects, unable to quickly evolve the complex internal respiratory systems like lungs, or the efficient circulatory systems like closed blood vessels that might have buffered the crisis, simply ran out of physiological options. They were too large to hide, too high maintenance to starve, and too dependent on diffusion to breathe. The most profound legacy of the Great Dying was the deep geological silence that followed. The ecosystems, once rich and diverse, became vastly simplified. On land, the vast, continuous forests were replaced by desolate, barren tracts interspersed with hardy, acid-tolerant fungi. Some evidence suggests fungi were the dominant life form for a period, feeding on the mountains of dead wood and organic matter that now, finally, began to decay. The aerial hunters, the meganeura, vanished entirely. Their high-energy, specialized niche was instantly rendered impossible by the physics of the low-oxygen, high CO2 air. Any remaining insects that survived this pulse were, almost without exception, small, generalist species. Their small bodies required minimal oxygen, were easier to hide and demanded less food, making them metabolically cheap and resilient against the chaos. The Permian-Triassic boundary in the geological record is marked by a sudden, severe drop in fossil diversity. It is the moment when life's great experiment with gigantism for arthropods was definitively terminated. The era of the scale trees, the deep swamps, and the supersaturated air was over. The Earth had hit the ultimate reset button. The subsequent period, the Triassic, would be defined not by the survivors' complexity, but by the sheer, terrifying ecological emptiness left behind. Life had been knocked back to its most basic elements, forced to slowly rebuild from the few hardy lineages that managed to endure the unparalleled global collapse. The lesson was brutal. Extreme specialization, even to the point of being the aerial apex predator, cannot withstand planetary-scale chaos. The Great Dying left a planet scarred and largely silent, but life, in its most tenacious forms, persisted. As the colossal arthropods vanished, a far less visible but infinitely more resilient lineage of insects inherited the devastated Earth. We turn now to examine the survivors' traits, the critical characteristics that allowed small, generalist species to endure the apocalypse, proving that in times of extreme crisis, resilience outweighs size. The survival of certain insect groups was not a matter of luck. It was a testament to their superior metabolic efficiency and physiological flexibility, traits that the specialized giants conspicuously lacked. The fundamental reason for the survival of the smaller arthropods, those perhaps only a few millimeters or centimeters long, is directly tied to the collapse of the atmosphere, specifically the dual crisis of hypercapnia and hypoxia. Lower oxygen demand. A tiny insect has a minuscule volume of tissue to support. Its overall resting metabolic rate is orders of magnitude lower than that of the 6-foot arthropleura. When the atmospheric oxygen levels dropped, the smaller body could still meet its minimal energy needs with the remaining air. The oxygen debt that choked the giants was easily managed by the small form's efficient CO2 venting. The smaller body has a profoundly more favorable surface area-to-volume ratio. This means that a large portion of the small insect's tissue is very close to the external spiracles and the skin's surface. Even when the external CO2 levels were dangerously high, the short diffusion distance allowed the small insects to vent their metabolic waste efficiently. They avoided the fatal internal acidification, hypercapnia, that paralyzed their colossal relatives. Essentially, the smaller insects were metabolically cheap. They could survive on less air and process waste more effectively, making them physiologically buffered against the extreme atmospheric changes that defined the Permian crisis. Beyond basic physics, the survivors exhibited crucial ecological traits that allowed them to navigate the poisoned, fragmented landscape dietary generalism. The giants were often specialists, reliant on specific types of moist, abundant Carboniferous flora. When that food source was destroyed by acid rain and drought, they starved. The surviving insects, by contrast, were often generalists, scavengers, detritivores, or opportunistic feeders. They could survive on decaying wood, fungi, spores, or the tough, less nutritious tissues of the new Permian gymnosperms. Their diets were flexible enough to exploit the meager, scattered resources of the post-apocalyptic world. Rapid life cycles, small insects typically possess short generation times and high reproductive rates. When environmental conditions fluctuated violently, alternating between heat, drought, and toxicity, these insects could breed quickly. This allowed them to adapt faster. Genetic mutations advantageous to survival, like increased heat tolerance or resistance to chemical toxicity, could spread through the population in a few generations. Enabling rapid evolutionary response outweighed the crisis. They could quickly repopulate areas after a localized disaster like a flood or fire, that might have instantly annihilated a slow-reproducing population of giants. Exploitation of microclimates. Small size grants the ability to utilize microclimates. The surviving insects could find shelter in tiny crevices deep beneath rocks or within the bark of the new conifers. These micro-refuges offered stable pockets of lower temperature and higher humidity, effectively insulating them from the lethal thermal and desiccation extremes that plagued the vast, exposed bodies of the giants, the survivors. Traits established a new evolutionary philosophy for insects. Miniaturization is the path to immortality. The post-Permian world was a harsh classroom that taught a definitive lesson. The risks associated with extreme size, high metabolic cost, dependence on atmospheric consistency, and slow reproduction are not worth the reward of being an aerial apex predator. The insects that endured, the ancestors of modern beetles, grasshoppers and true flies, carried the torch of life into the Triassic period. They were not impressive in size, but they were masterpieces of biological thriftiness. They possessed the structural simplicity, metabolic resilience, and reproductive agility to weather any future global crisis. The silent, desolate Earth that followed the Great Dying demanded efficiency, not magnificence. By reducing their size, the surviving insects maximized their ability to breathe, eat, reproduce, and hide. They proved that sometimes the most profound evolutionary success is achieved by being small enough to fit through the cracks of a collapsing world. They carried the blueprint for life forward, ready to slowly rebuild the biological diversity we know today. The colossal trauma of the Great Dying passed, leaving behind a profound emptiness. We move now into the Triassic period, the opening act of the Mesozoic era, where the Earth began the agonizingly slow process of rebirth. This was not an immediate blooming, but a gradual, cautious expansion of life into a world starved of biodiversity, creating a new evolutionary landscape defined by survival, scarcity, and, most importantly, opportunity for the small and the adaptable. For millions of years following the extinction pulse, the planet was stuck in the disaster fauna stage. The ecosystems were extremely simple, dominated by a few hardy, fast-reproducing generalist species, the same resilient insects and small vertebrates that survived the Permian chaos. The ecological pyramid, once towering and complex, was reduced to a flat, simple base. This scarcity, however, was the ultimate evolutionary gift to the survivors. The death of the giants created vast, open niches, eliminating the massive competitors and apex predators that had once governed the landscape. The key to the Triassic rebirth was the removal of the old constraints, removal of apex invertebrate predation. The meganeura were gone, and the massive predatory arthropods that fed on early vertebrates were eliminated. This immediately lifted the pressure for terrestrial vertebrates like early reptiles to remain small and hide. They could now begin to grow larger, exploring new body sizes and shapes that had been too risky in the age of the giants. Abundance of resources relative to competition. While resources were scarce in an absolute sense due to the damaged flora, the competition for those resources was almost non-existent. The small surviving insects had access to huge tracts of land and scattered food sources without facing a towering arthropleura descendant demanding the same forage. This lack of competition allowed the small, resilient insect populations to stabilize and slowly diversify. They could afford to specialize again, but this time they specialized in miniaturization and efficiency. The Triassic was a quiet, relentless period of insect innovation. Unburdened by the physical limitations of gigantism and fueled by their high reproductive rates, the surviving lineages explored new forms and new niches that would define their future. The rise of complete metamorphosis, holometabolism. Many key modern insect orders, like the ancestors of beetles, wasps and flies, began to truly diversify during this period. These insects use complete metamorphosis: egg, larva, pupa, adult, which is a masterpiece of efficiency. The non-feeding pupal stage allowed them to outweight the persistent environmental instability of the early Triassic, shielding themselves from lethal heat or drought. The specialized larval stage allowed them to gorge on specific, low-quality food like tough gymnosperm leaves, while the adult focused solely on reproduction and dispersal. This two-stage life cycle was a perfect fit for a stressful, resource-poor world. The development of new flight mechanics, the survivors, being small, perfected flight in the low-oxygen, low-density atmosphere. They evolved more powerful, compact flight muscles and more sophisticated wing articulation than the simple, massive wings of the meganeura. This new flight model prioritized agility and endurance over brute force, leading to the hyper-efficient flying machines we see today. Crucially, the resilience of the insect survivors allowed the entire terrestrial food web to recover. The insects, small as they were, performed the vital ecological services necessary for large-scale recovery. They became the primary pollinators, scavengers and detritivores in a world where efficient decay was desperately needed. The existence of a vast, if scattered, food source of small insects allowed the surviving small reptiles, the ancestors of the dinosaurs, to find enough consistent protein to fuel their growth. The dinosaurs would eventually rise to dominate the land, a magnificent evolutionary explosion that was made possible only because the tiny, resilient insects, the forgotten survivors of the great dying, had managed to keep the base of the food chain functioning during the crisis. The Triassic rebirth demonstrates that a mass extinction is not just an ending. It is a profound biological clearance sale. By removing the highly specialized, high-cost giants, the Earth created a blank slate. The subsequent success of the small, adaptable forms ensured not only the survival of the insects, but the future dominance of the entire vertebrate lineage. The age of the colossal arthropods was over, replaced by the age of quiet efficiency and profound diversification. As the Triassic rebirth progressed, the survivors of the Great Dying slowly began to rebuild the planetary food web. Yet this recovery introduced a profound new source of evolutionary pressure, one that permanently cemented the insect's path towards smallness and resilience: the looming presence of the dinosaur's shadow. The rise of the large vertebrates, the archosaurs and early dinosaurs, fundamentally changed the rules of competition, ensuring that gigantism in insects would never return. The vast ecological void left by the Permian extinction was an open invitation for any successful lineage to scale up. The small, resilient reptiles that survived the crisis seized this opportunity, evolving quickly into the dominant megafauna of the Mesozoic era. The competition for resources, the primary challenge these large vertebrates posed, was not just predation, but resource competition during the Carboniferous. The arthropleura and other giant arthropods were the primary large-scale herbivores, consuming massive amounts of foliage. In the Triassic, this role was taken over by increasingly larger herbivorous dinosaurs and reptiles. Imagine the difference: arthropod giant, a cold-blooded, segmented consumer, limited by the diffusion rate of oxygen and the mechanical inefficiency of its exoskeleton. Its consumption was high, but its movement was slow, allowing plants some time for recovery. Dinosaur giant, a large, likely warm-blooded or homeothermic consumer with a high-efficiency endoskeleton, active lungs, and a massive body capable of processing enormous quantities of tough, woody gymnosperm foliage. These emerging giants were metabolically superior competitors. They were faster, more powerful, and could strip a patch of vegetation far more rapidly and completely than any insect could. This competition squeezed the surviving herbivorous insects into ever smaller, more specialized niches, forcing them to feed on scraps, roots, or the internal tissues of plants that the mega herbivores could not easily access. The warm-blooded threat, speed and evasion. Even more critical was the evolution of vertebrate predation. The rise of the archosaurs and early, agile carnivorous dinosaurs presented a high-speed, high-efficiency threat that the former insect giants never faced. The meganeura dominated a world free of birds, bats, or speedy mammalian predators. Their greatest aerial challenge came from their own kind. The early dinosaurs, however, were developing warm-blooded metabolism. This allowed for sustained, high-speed locomotion and hunting independent of external temperature. They could hunt aggressively, day or night, agile limbs and jaws. Their internal skeletons allowed for rapid movement, swift pounces and powerful bites, making them highly effective ambush predators. For the vast, slow-moving bodies of any potential giant insect, this new threat was fatal. A giant arthropod would be a slow, irresistible target, a massive block of protein and fat, incapable of outrunning or effectively fighting off a streamlined, endothermic hunter. This new predatory regime imposed a clear and final selective pressure on the insects. Survival requires evasion and stealth. To avoid the dinosaur's shadow, insects had to become miniature. Small enough to hide under leaves, in crevices or within soil, completely invisible to a large predator. Evasive, fast enough to escape a sudden lunge, with small body mass allowing for instantaneous acceleration. Nocturnal. Many specialized in feeding and movement under the cover of darkness to avoid detection. The evolutionary rewards for attempting to grow large had entirely disappeared. Any insect lineage that attempted to push its size limits again, even if oxygen levels had marginally improved, would be instantly eliminated by a large passing reptile. Their colossal bodies would become nothing more than a momentary high-protein snack. The dinosaur's shadow permanently reset the evolutionary trajectory of the insect world. The age of invertebrate supremacy was irrevocably over. The ultimate success of the insects in the Mesozoic and Cenozoic eras was their strategic retreat into smallness and specialization. By becoming the world's masters of miniaturization, stealth, and resilience, they ensured their survival throughout the age of dinosaurs and beyond, proving that the most enduring life forms are those that avoid confrontation entirely. We leave the catastrophic eras of the Permian and the slow emergence of the Triassic and shift our focus to the enduring physics of the air itself. The extinction of the giants fundamentally and permanently altered the relationship between insect and atmosphere. We must now compare the ancient atmospheric conditions that permitted colossal flight with the modern air pressure and density that restrict insects to their current, smaller scale. This contrast reveals how the very physics of flight changed forever. To understand flight, we must understand air density. Air density is a measure of the mass of air molecules packed into a given volume. This density dictates two critical forces for flight: lift, the upward force generated by the wings, and drag, the resistance felt by the object moving through the air. In the Carboniferous Period, air was fundamentally different. High oxygen concentration, at around 35% oxygen, the air was metabolically high octane, allowing the massive flight muscles of the meganeura to be supercharged, overcoming the limitations of the tracheal system. Higher density, lift and drag. While atmospheric pressure might not have been vastly different from today, the ancient air composition, likely combined with higher humidity and the physical consequence of the vast vegetation, resulted in an overall denser medium. For a creature like the colossal meganeura, this dense, rich air was a magnificent partner. Easy lift, the wings encountered significant molecular resistance with every downward stroke, generating immense lift relative to the effort required. This density was a crucial mechanical support for lifting the creature's immense, heavily armored body mass. Stable movement. High drag in thick air tends to stabilize flight, making the movements of the large wings more predictable and controlled. The meganeura was a powerful, but perhaps somewhat clunky flying machine, whose success relied on the sheer quantity and density of the air molecules it encountered. Today, the atmosphere is a product of post-Permian stability. The geological burial of carbon has ceased on the massive scale seen before, and the composition has settled at roughly 21% oxygen and a far lower, stable density. This modern air presents a significant mechanical challenge to large insects. Lower lift. When a modern dragonfly beats its wings, it encounters less molecular resistance. To generate the same lift as the meganeura, it must move its wings faster, change their pitch more radically, or beat them over a greater distance. This requires a much higher frequency of wing beats and greater internal energy expenditure. Increased power requirement, miniaturization. Any modern insect attempting to grow to the size of the meganeura would face an insurmountable aerodynamic hurdle. The power required to move its mass in the modern, thinner air, measured as mass-specific power output, would exceed the absolute physical capacity of its flight muscles. The thinner the air, the harder the small muscles have to work, and the larger the muscles must be relative to the body, until the point where the creature is nothing but muscle, with no room for a brain or reproductive organs. The permanent drop in oxygen and density ensured that insect gigantism became aerodynamically impossible. The surviving lineages of the Triassic and Jurassic, the ancestors of modern insects, were those that perfected a new style of flight based on aerodynamic efficiency and agility, rather than brute power and high lift. Miniaturization. By shrinking, they drastically reduced their wing loading, the ratio of body weight to wing area. A smaller, lighter body is much easier to lift in low-density air. Sophisticated wing movement. Modern insects, particularly flies and bees, use incredibly complex, non-linear wing movements, flapping, rotating, and twisting the wing surfaces to create miniature, powerful vortices of air that generate lift more efficiently than the simple, powerful strokes of the ancient giants' metabolic efficiency. They evolved internal mechanisms to quickly move and utilize the limited oxygen, allowing them to sustain high-frequency wing beats necessary for modern agility. The comparison is clear. The meganeura was a colossal, high-lift cargo plane dependent on a specific, powerful atmospheric environment. Modern insects are high-precision, acrobatic fighters, capable of phenomenal speed and maneuverability through sheer physical mastery of the environment. Not just reliance on its abundance, the physics of flight permanently restricted insects to the realm of the small. The modern atmosphere is simply too demanding, too low in lift and fuel to allow the colossal, diffusion-limited bodies of the giants to soar again. Their demise was cemented by geological events, but their absence is a continuous fact of modern aerospace physics. We step now far forward in time, traversing hundreds of millions of years, past the age of dinosaurs and into the recent geological past, the Quaternary Period, the era of the Ice Age cycles. While these cycles occurred long after the initial Permian catastrophe that eliminated the giant insects, they serve as a profound final lesson in the fate of insect size, demonstrating how persistent climate instability permanently reinforced the evolutionary pressure towards smallness and rapid adaptation. The Ice Ages were not periods of continuous, unbroken cold. Rather, they were a series of massive, rhythmic oscillations between long, cold glacial periods when vast ice sheets covered large portions of the continents and shorter, warmer interglacial periods, like the one we live in now. This instability was driven by subtle shifts in Earth's orbit and axial tilt, known as Milankovitch cycles. For insects, this constant, predictable, yet extreme climate fluctuation provided a stress test that ensured the evolutionary blueprint established in the Triassic, the blueprint of the small and the efficient, was continually perfected. The challenges posed by the ice ages, though different from the volcanic crisis of the Permian, were equally hostile to gigantism, metabolic shutdown, the cold. During the cold glacial periods, temperatures plummeted across vast territories. As ectotherms, cold-blooded creatures, insects' activity is directly tied to external temperature. A large insect, with its massive body volume, takes an incredibly long time to warm up and become active, even in a brief, sunny spell. A smaller insect, with its high surface area-to-volume ratio, can absorb solar radiation quickly, reaching operational temperature faster. The extreme cold periods favored life that could achieve metabolic efficiency with minimal warming time. Habitat loss and fragmentation. The growth and retreat of the continental ice sheets constantly fragmented and reshaped habitats. Forests were replaced by tundra, and tundra was replaced by forest, all over timescales of tens of thousands of years. This volatility meant that large, specialized populations, like those required to maintain giant dimensions, could not become entrenched. They required vast, stable territories to sustain their low reproductive rates. The boom and bust cycle. The rapid switch between glacial and interglacial conditions created ecological boom and bust cycles. Interglacial warm periods offered abundant resources, encouraging growth, but these periods were always short-lived. A return to the glacial cold would crash the food web, favoring only those species with rapid reproductive cycles, species that could reproduce multiple generations and migrate vast distances during the brief boom phase. This recurrent instability provided a continuous selective filter, ensuring that the evolutionary advantage was always tilted toward resilience and adaptability. Dormancy and diapause. Small insects perfected strategies to survive the cold, such as diapause, a state of arrested development, or overwintering in eggs or larvae, often utilizing small, protected microclimates in the soil or under bark. A giant insect could not effectively enter or sustain such a deep, prolonged state of dormancy. Its massive body required too much energy to maintain basic cellular integrity through a long, deep freeze dispersal power. The smaller, more efficient flying insects developed the ability to disperse rapidly over vast distances, tracking the advancing and retreating climatic zones. Their lightweight and refined flight mechanics, as discussed in the previous chapter, made them highly mobile, capable of surviving habitat loss by simply flying over the newly established ice barriers or expanding deserts. The Ice Age cycles thus served as a planetary editor, continually trimming away any lineage that attempted to revert to the high-cost, high-maintenance physiology of the past. If a lineage of insects managed to evolve to even half the size of the meganeura during a particularly long, warm interglacial period, the inevitable return of the glaciers would deliver a final, decisive selective wave favoring the small, the quick, and the metabolically cheap. The stability of our modern small insects is a direct result of these long ages of environmental trauma. They are survivors, perfectly engineered to be flexible and low-cost, demonstrating that after the Permian extinction stripped away their giant size, the Ice Age cycles ensured it would never be worth the risk of growing large again. We move now past the age of dinosaurs into the Cenozoic era, the age of mammals and birds, our own time. While the great climate catastrophes had long since eliminated the giant insects, the rise of warm-blooded life introduced a profound, persistent evolutionary pressure that permanently reinforced the insect's commitment to smallness and agility. This was the establishment of the warm-blooded threat. Thus, primary difference between the predators of the Carboniferous and those of the Cenozoic lies in metabolism and mobility. The ancient arthropod, Giants faced cold-blooded ectothermic predators, slow, often sluggish reptiles and amphibians whose speed and activity levels were dictated by the external temperature. This left the giants with windows of safety during cold nights or shaded hours. The mammals and birds that diversified after the extinction of the dinosaurs, however, are endotherms, warm-blooded. They maintain a high, constant internal body temperature, allowing their muscles and nerves to operate at peak efficiency, regardless of the environment. This fundamental metabolic advantage translated into two lethal pressures on any insect attempting to grow large: sustained pursuit and night hunting. Unlike their ancient counterparts, mammals and birds can hunt relentlessly and continuously, day or night, rain or shine. Their high metabolism allows for sustained high-speed pursuit that would have been physically impossible for the giant, low-oxygen-fueled predators of the Permian. The insect world lost its thermal safe zones. A giant, slow-moving arthropleura descendant would have been a visible, high-caloric target 24 hours a day, unable to hide effectively in the face of persistent mammalian foraging. Precision and efficiency. Birds, in particular, evolved into aerial masters, possessing acute vision, powerful, high-frequency wing beats, and complex navigation skills. They filled the exact aerial niche once dominated by the meganeura, but with infinitely superior technology. Any large, slow-flying insect would be instantly outmatched, unable to maneuver or outrun a raptor or a swift. The risk of predation became an absolute certainty for a large insect. The warm-blooded threat highlighted the unbridgeable metabolic disparity between the arthropod and the vertebrate blueprint. Vertebrate, highly efficient lungs and a 4-chambered heart actively deliver vast amounts of oxygen to the tissues, fueling explosive and sustained activity. Arthropod relies on passive diffusion via the tracheal system, leaving its speed and energy reserves dependent on the thin, external atmosphere. Any hypothetical large insect emerging in the Cenozoic would have been a metabolic paradox. A slow-motion prey item in a world of high speed. Warm-blooded hunters imagine a modern squirrel. Its lightning-fast reflexes and tiny size are a perfect defense against most threats. Its size is a consequence of the need to be quick and small. The surviving insects, by necessity, mirrored this strategy. They became too small to provide a rewarding meal and too fast to be caught easily. The presence of warm-blooded hunters forced insects into even more specialized niches of stealth and invisibility. Burrowing and hiding. Many insect groups perfected the art of spending their vulnerable larval stages hidden deep within soil, wood, or water, emerging only as fully formed, highly mobile adults. Taste and toxicity. Others evolved chemical defenses using foul-tasting compounds or bright, aposematic, warning, coloration to signal to birds and mammals that the caloric reward was not worth the physiological cost of eating them. Miniaturization. As stealth, by far the most successful strategy was continuing the trend of miniaturization. A tiny weevil or fly simply doesn't register on the metabolic radar of a large mammal. It is too small, too elusive, and costs too much energy to pursue. The warm-blooded threat served as the final, enduring check on insect size. It ensured that even if a future geological event were to briefly raise oxygen levels, the evolutionary advantage would remain firmly with the small. The cost of carrying a large, low-efficiency body in a world ruled by high-speed, high-efficiency predators became insurmountably high. The insect's great success in our world is a direct result of their strategic retreat from size, a necessity imposed by the fast, relentless pace of the mammalian age. The story of the giant insects ends not in catastrophe, but in a profound evolutionary triumph of the opposite extreme, miniaturization. In the modern world, dominated by the warm-blooded threat and constrained by the physics of low-oxygen air, being small is no longer a physiological limitation, it is the ultimate strategic advantage. We explore now the critical benefits that make the vast majority of today's insects the most successful. Numerous and enduring animal group on Earth, speed, stealth, and low overhead. The success of modern insects is rooted in their mastery of the principle of thrift. They have perfected the art of doing more with less, turning their small scale into a powerful suite of defensive and reproductive tools that the ancient giants could never possess. For the giant arthropods, metabolic maintenance was astronomical. Their existence was a continuous struggle to consume enough high-quality food simply to support their body mass. Small insects, by contrast, are incredibly cheap to run. Minimal caloric demand, a tiny insect requires only a fraction of the calories, water, and space needed by a large creature. They can subsist on scattered ephemeral resources, a single drop of nectar, a decaying leaf, or a tiny particle of fungus. This allows them to thrive in virtually any environment, from polar ice caps to arid deserts, by exploiting micro pockets of sustenance that are invisible to large vertebrates. Reduced water loss. We know that the tracheal system is inefficient at retaining water. By shrinking, insects minimize their surface area to volume ratio, drastically reducing the evaporative surface exposed to the environment. This simple geometric principle makes them masters of water conservation, allowing them to survive the extreme aridity that defeated the massive, water-leaking bodies of the Permian giants. Ecosystem resilience. Because they demand so little, small insects are highly resilient to ecological collapse. If a food source disappears, they can immediately switch to another or enter diapause, a form of hibernation, until conditions improve. A flexibility denied to creatures with immense, non-storable energy needs. In the era of warm-blooded predators, fast, efficient, and constantly active, survival hinges on the ability to escape detection or evade capture. Miniaturization provides this escape velocity, instantaneous acceleration. A small body has low inertia. This means its flight muscles can generate instantaneous, explosive bursts of speed. A fly can execute sudden, sharp turns and accelerations, often referred to as escape trajectories, that overwhelm the reaction time of a larger predator, like a bird or a mammal. The giant meganeura was a powerful, slow-reacting machine. Modern insects are nimble, high-G acrobats. Mastery of turbulence. In the turbulent, shifting air currents of the modern world, large wings struggle. Small insects, however, have developed sophisticated, high-frequency wing beats and complex wing-to-body ratios that allow them to navigate these microcurrents with precision, making them unpredictable and virtually uncatchable. Stealth and invisibility. The most effective defense is simply not being seen. Small size allows insects to utilize the world's most ubiquitous defense system, hiding. They can spend their entire lives concealed within bark, under stones, inside soil, or beneath the water's surface, remaining completely invisible to the large visual systems of birds and mammals. Perhaps the most potent advantage of small size is its link to reproduction and evolutionary speed. Short generation. Time. Most small insects have extremely short life cycles, often completing a generation in weeks or even days. This rapid turnover is a massive evolutionary advantage. Quick adaptation. When a new selective pressure arises, like a new pesticide, a disease, or a change in local climate, beneficial genetic mutations can spread through the entire population in a matter of months, not the millions of years required for the great reptiles or mammals. Population recovery. After a local catastrophe, e.g., a drought or localized fire, high reproductive rates allow the small insect population to recover immediately. quickly filling the damaged niche before a slower reproducing species can react. High fecundity. Small size allows insects to produce a massive number of offspring, high fecundity. This ensures that even if 99% of the population is lost to predation or disease, the surviving 1% can instantly restart the population the following season, guaranteeing the survival of the lineage. Miniaturization is thus not a fallback position. It is the pinnacle of evolutionary fitness in a fluctuating, dangerous, and competitive world. The giant insects were magnificent, but they were fragile and slow to adapt. Modern insects are the embodiment of ecological victory through humility, demonstrating that the best strategy for enduring planetary time is to be tiny, fast, cheap, and capable of infinite, rapid reinvention. We have explored the arc of life from the colossal, oxygen-drenched world of the meganeura to the lean, efficient world of modern insects. As we near the conclusion of our journey, we must revisit the central question that began this exploration, the oxygen-size relationship. We will now summarize the current scientific understanding of this delicate balance and appreciate the profound stability of the modern atmosphere, the air that now surrounds you. The demise of the giant insects and the survival of the small has provided scientists with a massive planetary-scale experiment, allowing them to precisely map the physiological constraints imposed by atmospheric oxygen. Decades of research have confirmed that while predation, competition, and climate change all contributed to the timing of the giant's extinction, the absolute physical limit on insect size is the partial pressure of oxygen available for diffusion. The simple, elegant structure of the tracheal system, its reliance on passive gas diffusion, is the unyielding biological reality. As the global atmosphere dropped from the Carboniferous high of 35% down toward the Mesozoic mean of 21%, the physical constraint of oxygen delivery rapidly compressed the maximum viable size for arthropods. At 35% O2, the diffusion gradient was steep enough to sustain the thick muscle masses required by 2-foot wingspans and 6-foot bodies. At 21% O2, modern, the diffusion gradient is significantly shallower. This level can only efficiently supply small volumes of tissue within a very short distance of the spiracles. Any insect attempting to grow substantially beyond a few centimeters in thickness will find its core tissues starved for the energy needed to operate. This realization has led to powerful predictive models. Scientists can now accurately calculate the maximum theoretical size of an insect based on atmospheric oxygen concentration and the geometry of its tracheal tubes. These models confirm that the oxygen levels maintained throughout the Mesozoic and Cenozoic eras are simply too low to support the massive, diffusion-limited bodies of the ancient giants. The atmosphere you are breathing now is not just thin. It is profoundly stable and biologically balanced. For the last 65 million years, since the end of the dinosaur age, oxygen has remained remarkably consistent, settling around the 21% mark. This stability, a consequence of the current, efficient global carbon cycle where modern decomposers, fungi and bacteria efficiently recycle dead matter. Preventing vast carbon burial is a profound evolutionary virtue. Why is 21% O2 the perfect stabilizer for smallness? Metabolic safety margin. The 21% level is just high enough to sustain the high metabolic rates of modern life, mammals and birds, but it offers absolutely no excess capacity for diffusion-limited giants. It is a precise, planetary sweet spot that locks in the advantage of the small and efficient. No more hypercapnia. The modern concentration of carbon dioxide, currently around 420 ppm, is vastly lower than the lethal Permian levels, 3,000 to 10,000 ppm. This ensures that the small insects, with their efficient surface-to-volume ratio, have no issue venting CO2, permanently removing the hypercapnia crisis from the table. Predictable conditions, the stability of the oxygen level, coupled with the recurring predictable constraints of the Ice Age cycles, means that the evolutionary rule has become immutable. Invest in agility and defense, not size. The oxygen debate, therefore, has evolved from a simple question of cause to a complex understanding of constraint. The meganeura was killed by a perfect storm of geological events, but its subsequent non-return is a continuous function of physics. The stability of our modern 21% atmosphere is the silent, ongoing guarantee that the age of invertebrate gigantism is permanently over. The air you breathe is the reason you can sleep soundly, knowing that the greatest evolutionary challenge you face will not be a 3-foot dragonfly emerging from the shadows. The small, quick insects that remain are the most successful life forms on Earth precisely because they learned the ultimate lesson: to endure. You must accept the world's limitations, not rely on its transient excess. We have established the enduring constraints that prevent the return of the colossal arthropods. Yet, even in our modern low-oxygen world, life always seeks to test the limits. Our final analysis on size takes us into the present day to examine the magnificent, albeit modest, creatures that represent the absolute maximum size achievable under current atmospheric and biological law, the world's largest bugs today. These champions of modern gigantism, such as the massive Goliath beetle of Africa, the immense Queen Alexandra's birdwing butterfly of Papua New Guinea, and the heavy giant wheater of New Zealand, are not mere large insects. They are living proof of the precise constraints of the 21% oxygen atmosphere. The Goliath beetle, Goliathus goliatus, is one of the heaviest insects on Earth. Capable of reaching lengths of over 4 inches, the sheer mass and thickness of its body present the most challenging structural test to the tracheal system, the tracheal tightrope. For the Goliath beetle, every millimeter of thickness represents a struggle against the law of diffusion. To sustain its substantial body volume and its powerful flight muscles, the beetle must dedicate a huge proportion of its internal structure to the tracheae, the air tubes. There is almost no internal space wasted. Its size is only possible because its overall shape remains relatively compact, ensuring that no internal cell is too far from a primary air supply. Metabolic trade-off. The beetle's colossal size also means that its metabolism is relatively slow compared to a tiny housefly. It is generally less agile and relies on immense armor and strength rather than speed for survival. This is the modern compromise. To be large, they must sacrifice the hyper-efficiency of their smaller cousins. The Queen Alexandra's birdwing, Ornithoptera alexandrae, is the largest butterfly in the world, with a wingspan that can exceed 11 inches. This creature tests the aerodynamic limits of flight in our low-density air. Wing loading challenge. To lift its comparatively heavy body with such large wings in low-density air, the birdwing must be a master of flight efficiency. Its wing shape is exquisitely optimized to generate the maximum possible lift, oxygen demand for flight. The flight muscles must work incredibly hard to move those large wings without the benefit of the 35% oxygen hypercharge that fueled the ancient meganeura. This is why the birdwing, despite its size, is not a predator and often relies on slow, soaring flight patterns to conserve energy. It is a spectacular creature, but its aerial maneuverability is limited by the available atmospheric fuel. The giant wheater, Danacrida spp, is a massive, flightless insect endemic to New Zealand. Some individuals are so heavy they weigh more than a mouse. The wheater is unique because by becoming flightless, it removes the energetic cost of flight, allowing it to redirect that energy into sheer body mass. Gravity and insulation. The wheater's heavy, terrestrial existence allows it to concentrate its size along the ground, where gravity is less of a factor on its limb joints compared to a flying insect. Its bulk also helps it retain heat in the cooler environments it inhabits. Ecological niche. It thrives primarily in island ecosystems, where the warm-blooded threat of mammalian predators was historically absent until humans introduced them. This lack of high-speed predation allowed it to evolve a slower, heavier life cycle without being constantly hunted. The presence of these colossal modern insects reinforces the final, permanent verdict of the Permian extinction. Maximum viable size is fixed. The largest insects today are pushing the absolute biomechanical and diffusion limits of the 21% oxygen ceiling. None can approach the bulk or wing size of their ancient counterparts. Trade-offs are mandatory. Modern giants must make severe trade-offs. Either they become extremely slow and heavy, like the waiter or Goliath beetle, or they become delicate, slow flyers like the birdwing. They cannot be both colossal and highly agile aerial predators, which was the definition of the meganeura. No room for error. The successful existence of these largest insects is often precarious, relying on highly stable or isolated environments, like the islands for the waiter. Any significant drop in oxygen or rapid increase in temperature would immediately threaten their viability, proving they still live on the very edge of the diffusion threshold. The echoes of gigantism remind us that while the pursuit of size is an innate evolutionary drive, the Earth's current atmosphere has erected an insurmountable barrier. The insects of today are not failures. They are master engineers who have perfected their design within the most restrictive physical parameters possible, demonstrating that true victory is found in the art of the perfect compromise. We have journeyed through millions of years of atmospheric extremes, witnessed the geological violence of the Siberian traps, and charted the relentless quiet efficiency of miniaturization. Now, as the final echoes of the giant wings fade, we conclude our exploration by reflecting not on the death of the colossal insects, but on their profound and lasting influence. The legacy of the unseen architects left in the dust of deep time. The giant arthropods of the Carboniferous and Permian may be gone, but the very existence of our modern world is built upon the environmental conditions they created and the evolutionary lessons learned from their extinction. Their time on Earth was not a failed experiment. It was a crucial, transformative phase of planetary engineering. The giants and the specialized ecosystem they inhabited were responsible for two immense, world-shaping acts: the fueling of modern industry. The colossal, non-decaying swamp forests that fed the giants, the very engine that drove oxygen to 35%, were compacted into the coal seams of the Carboniferous Period. This ancient, buried organic material remains even today the most significant carbon sink in the Earth's history. The industrial age, the technologies that support billions of people, and the very energy that powers the lights in your home are all derived directly from the geological mausoleum created by the giant plants and insects of that ancient time. They provided the foundation of modern fuel by locking away carbon on a global scale. The testing of biomechanics. The giants pushed the arthropod body plan to its absolute, non-negotiable physical limits. Their demise, caused by the failure of the tracheal diffusion system at colossal size, provided the ultimate proof of evolutionary constraint. This irreversible lesson solidified the path for all future insects toward smallness, agility, and the mastery of metamorphosis. Modern insects, masters of efficiency, are only so successful because the giants failed so spectacularly. The story of the giant insects offers a profound lesson in the fragility of specialization and the virtue of resilience. The meganeura was a perfect machine, but it was perfectly tuned to a temporary extreme world. When the planet returned to a more balanced, moderate state, its specialized efficiency became a fatal weakness. The long reign of the giants reminds us that biological success is ultimately not measured by size, but by the capacity to endure volatility. The survivors, the small, adaptable, metabolically frugal forms, proved that the truest evolutionary strength lies in the ability to downsize, hide, and reinvent quickly, ensuring that life, in some form, always persists through catastrophe. In a deeper sense, the giants were the unseen architects of the modern insect world. Every tiny beetle you might see, every swift-flying mosquito, is a living descendant carrying the successful traits honed in the desperate aftermath of the Great Dying. They possess the flight agility, the small body mass, and the low metabolic rate required to thrive in a world ruled by the physical laws that destroyed their ancestors. The quiet complexity of the modern world, the intricate food webs, the flourishing of birds and mammals, the stability of the atmosphere at 21% O2 is all built upon the vast, silent ecological space that the giants vacated. They defined the constraints, they fueled the future, and then they stepped aside, allowing life to restart on a more modest, yet infinitely more robust foundation. As you drift now, let the imagination rest on the immense scale of time. The air you breathe is the quiet, stable echo of the past, and the silent dust of the ancient giants is woven into the very fabric of our enduring planet. If you found peace and wonder in this journey through deep time, please consider supporting Tierra Hueca by giving this video a like, subscribing to the channel for more calm explorations into the mysteries of the Earth, and sharing your thoughts in the comments below. We are grateful you chose to spend this time with us. Sleep well, traveler.